including intense radiation bursts and the accretion of stellar material, shedding light on the dynamics of galactic cores. Unlike the Milky Way, Andromeda's spiral arms are relatively well-defined, giving it a classic pinwheel appearance. These arms are teeming with regions of active star formation, where immense clouds of hydrogen gas collapse under their own gravity to form new stars. The galaxy's bright blue clusters, seen in ultraviolet light, are a testament to the ongoing birth of massive, short-lived stars that will eventually explode as supernovae. The older, reddish stars in Andromeda's halo and central bulge tell a different story, one of ancient star systems that have weathered billions of years. These populations provide a glimpse into the early epochs of galactic evolution, helping scientists piece together the history of star formation in our local universe. Perhaps the most tantalizing aspect of the Andromeda galaxy is its impending collision with the Milky Way. Observations reveal that Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In approximately 4.5 billion years, the two galaxies are expected to merge in a spectacular cosmic dance, forming a new elliptical galaxy sometimes referred to as Milkomeda. This collision will be a transformative event, reshaping the structure of both galaxies and igniting a burst of star formation as gas and dust clouds collide. Although such a cataclysm might sound destructive, the vast distances between stars mean that direct stellar collisions are unlikely. Instead, the merger will create tidal tails, intricate streams of stars, and a dramatic reshuffling of galactic components. Andromeda has been studied extensively using both ground-based and space-based telescopes. The Hubble Space Telescope has provided breathtaking images of the galaxy, revealing its intricate spiral structure, star-forming regions, and even individual stars. Future observatories, such as the James Webb Space Telescope and the Extremely Large Telescope, promise to deepen our understanding of Andromeda by studying its stars, planets, and black hole in unprecedented detail. One of the most exciting areas of research involves the search for exoplanets in Andromeda. While detecting planets in another galaxy is extraordinarily challenging, advancements in microlensing techniques and spectroscopy may one day allow us to identify worlds orbiting stars in this neighboring galaxy. Such discoveries could revolutionize our understanding of planetary systems and the potential for life beyond the Milky Way. Andromeda's proximity makes it a valuable reference point for studying galaxies throughout the universe. By examining its structure, composition, and dynamics, astronomers can develop models that apply to galaxies billions of light-years away. The study of Andromeda's dark matter halo, for instance, has implications for understanding the mysterious substance that makes up 85% of the universe's mass. The galaxy also serves as a time capsule, preserving evidence of past interactions with other galaxies. Stellar streams, faint trails of stars torn from satellite galaxies, crisscross Andromeda's halo, offering clues about its history of galactic cannibalism. These remnants of past mergers help astronomers reconstruct the timeline of Andromeda's growth, providing a glimpse into the life cycle of galaxies. Beyond its scientific value, the Andromeda galaxy has captured the human imagination for centuries. Visible to the naked eye as a faint smudge in the night sky, it has inspired countless myths, artworks, and dreams of intergalactic travel. As our technology advances and our understanding of the cosmos deepens, Andromeda remains a symbol of humanity's insatiable curiosity and our quest to comprehend the universe. Whether through the lens of a telescope or the imagination of a dreamer, the Andromeda galaxy invites us to ponder profound questions about our place in the cosmos. What stories do its stars tell? What secrets lie hidden within its vast expanse? And what future awaits as our two galaxies converge in a cosmic embrace? The Andromeda Galaxy, or Messier 31, stands as one of the most intriguing and vital cosmic neighbors of the Milky Way. Its staggering proximity of 2.5 million light-years allows astronomers to explore its intricate structure with unprecedented clarity, a window into the processes that govern galaxies across the universe. This massive spiral galaxy, over 220,000 light-years in diameter, surpasses our own Milky Way in size and contains an estimated 1 trillion stars. Its colossal mass and dynamic nature make it a perfect laboratory for studying galaxy formation, star evolution, and the mysterious force of dark matter. Andromeda's double nucleus, a feature visible in its central bulge, has perplexed scientists for decades. This peculiar structure hints at a complex history of mergers and interactions with smaller galaxies. At its core lies a supermassive black hole, approximately 140 million times the mass of the Sun. This black hole exerts a gravitational pull that influences the orbits of nearby stars and triggers high-energy phenomena such as X-ray flares. These intense bursts of radiation illuminate the dynamic and sometimes violent processes that occur in galactic cores. Clouds collapse under gravity to form new stars. Bright blue clusters dot these arms, signifying the presence of massive, young stars that shine intensely before exhausting their fuel and ending their lives in spectacular supernovae. These explosions enrich the galaxy with heavy. The spiral arms of this galactic giant are regions of immense activity, where dense molecular elements, driving the chemical evolution necessary for the formation of planets and, potentially, life. The interstellar medium of Andromeda is also rich with hydrogen gas and cosmic dust, creating vibrant nebulae that serve as the birthplaces of new stars. Unlike our Milky Way, which exhibits a more subtle spiral pattern, Andromeda's arms are well-defined, giving it the iconic shape often associated with galaxies. These arms are not static, they are shaped and reshaped by the gravitational interactions with Andromeda's satellite galaxies. Observations reveal that Andromeda is surrounded by a swarm of smaller galaxies, some of which are being torn apart by its gravitational pull. These interactions create streams of stars, known as tidal tails, that arc through Andromeda's halo, providing clues about its history of mergers and acquisitions. Andromeda is not only a showcase of stellar life and death, but also a treasure trove of ancient stars. Its halo contains some of the oldest stars known, remnants from the earliest epochs of galactic formation. By studying these ancient stellar populations, scientists can trace the history of Andromeda back billions of years, uncovering the conditions that prevailed when the universe was young. These studies also shed light on the processes that shaped our own galaxy, offering a broader context for the evolution of the cosmos. One of the most captivating aspects of Andromeda is its future collision with the Milky Way. Observations of its motion indicate that it is hurtling toward us at a speed of approximately 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge to form a new, larger galaxy. This event, often described as a galactic dance, will dramatically reshape the structure of both galaxies. Stars, gas, and dark matter will be redistributed in a complex interplay of gravitational forces, creating tidal streams and igniting bursts of star formation. Despite the seeming violence of such a merger, the vast distances between individual stars mean that direct collisions between them are unlikely. Instead, the merger will create a new cosmic entity, sometimes referred to as Milkomeda, with an elliptical structure and a new center of mass. The Andromeda Galaxy has been the focus of numerous scientific missions and observations. The Hubble Space Telescope has provided some of the most detailed images of its structure, capturing its spiral arms, central bulge, and outer halo with stunning clarity. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other spiral galaxies in the universe. Advanced instruments, such as the James Webb Space Telescope, promise to unveil even more secrets, allowing astronomers to study the galaxy's individual stars, planetary systems, and even its dark matter halo with unprecedented precision. The search for exoplanets within Andromeda is a burgeoning field of study. While detecting planets in another galaxy is extraordinarily challenging, techniques such as gravitational microlensing offer a glimpse into this possibility. These methods rely on the bending of light caused by the gravitational field of a planet or star, revealing the presence of celestial objects that would otherwise remain hidden. Discovering exoplanets in Andromeda could revolutionize our understanding of planetary formation, potentially revealing worlds vastly different from those in the Milky Way. Andromeda's immense halo of dark matter extends far beyond its visible disk, influencing the motion of its stars and satellite galaxies. This unseen component constitutes the majority of the galaxy's mass, yet its nature remains one of the greatest mysteries in astrophysics. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock the secrets of this enigmatic substance, which plays a crucial role in the formation and evolution of galaxies throughout the universe. As the largest galaxy in our local group, Andromeda serves as a cosmic mirror, reflecting the processes that govern galaxies on larger scales. Its intricate structure, active star-forming regions, and dynamic interactions with other galaxies provide a microcosm of the universe's complexity. By studying Andromeda, astronomers gain insights into phenomena that apply to galaxies billions of light-years away, bridging the gap between our local universe and the distant cosmos. The Andromeda Galaxy is not just an object of scientific inquiry, it is a source of inspiration and wonder. Its visibility to the naked eye as a faint smudge in the night sky has captivated observers for centuries, from ancient astronomers who catalogued it as a nebula to modern scientists who unravel its mysteries with cutting-edge technology. Andromeda represents humanity's enduring quest to understand the cosmos, a testament to our curiosity and imagination. The Andromeda Galaxy is a beacon of cosmic curiosity, continuously drawing the gaze of astronomers and dreamers alike. Its vastness and complexity defy easy understanding, inviting deeper exploration with every new discovery. This galactic giant is not just a collection of stars, gas, and dark matter, it is a storybook of the universe itself, containing chapters that span billions of years and countless transformations. The study of Andromeda has provided humanity with unparalleled insights into the life cycles of galaxies. Its close proximity makes it an ideal target for research, as we can observe its individual stars and clusters with remarkable clarity. Scientists have identified diverse stellar populations within Andromeda, each with unique characteristics and histories. From the bright, young blue stars of its spiral arms to the ancient, red stars in its halo, every stellar population tells a different part of the galaxy's story. These stars are not just cosmic objects, they are timekeepers, offering clues about the conditions that shaped Andromeda over its lifetime. Andromeda's history is written in the light of its stars, but it is also etched in the faint streams of material that surround it. These tidal streams are the remnants of smaller galaxies that were torn apart and absorbed by Andromeda's gravity. By mapping these streams, astronomers can reconstruct the galaxy's dynamic past, piecing together the cosmic interactions that have shaped its structure. Each stream represents a merger, a collision, or a gravitational tug-of-war that occurred millions or even billions of years ago. Together, they form a mosaic of Andromeda's evolutionary journey, providing a glimpse into the violent processes that drive galactic growth. The role of dark matter in Andromeda's formation and evolution cannot be overstated. This invisible, enigmatic substance makes up the majority of the galaxy's mass, yet its true nature remains one of the greatest unsolved mysteries in modern science. Dark matter does not emit or absorb light, making it undetectable through conventional means. However, its presence is inferred from its gravitational effects on visible matter. In Andromeda, dark matter forms an extensive halo that stretches far beyond the galaxy's luminous disk, influencing the motion of its stars and satellite galaxies. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock clues about the fundamental composition of the universe itself. Andromeda's future is as fascinating as its past. The impending collision with the Milky Way is not just an event of local significance, it is a cosmic spectacle that will reshape the local group of galaxies. This merger will occur over billions of years, beginning with subtle gravitational interactions that will distort the shapes of both galaxies. As the two spiral galaxies draw closer, their stars will form tidal bridges, connecting the two systems in a gravitational embrace. Gas clouds will collide, triggering bursts of star formation and creating brilliant nebulae that will light up the night skies of any planets within these galaxies. Eventually, the two galaxies will merge into a single, massive elliptical galaxy, a testament to the transformative power of gravity on cosmic scales. While the prospect of this collision may seem daunting, it is a reminder of the dynamic and ever-changing nature of the universe. Galaxies are not static islands of stars, they are constantly interacting, merging, and evolving. The Andromeda-Milky Way collision will not only reshape the structure of these galaxies but also provide a unique opportunity to study the processes that drive galactic evolution. For astronomers billions of years in the future, this event will be a natural laboratory for understanding the interplay of gravity, dark matter, and interstellar gas. The Andromeda Galaxy has also inspired humanity to think beyond our own cosmic neighborhood. The possibility of life in Andromeda, while purely speculative, raises profound questions about the nature of the universe and our place within it. If planets orbit stars in Andromeda, and there is no reason to believe they do not, then the potential for life beyond the Milky Way becomes a tantalizing prospect. While the vast distances between galaxies make direct exploration unlikely for the foreseeable future, the study of Andromeda fuels our imagination and drives the development of new technologies that may one day bring us closer to answering these profound questions. Telescopes have played a crucial role in our understanding of Andromeda, transforming it from a faint smudge in the night sky to one of the most studied objects in the universe. Ground-based observatories equipped with advanced adaptive optics systems have provided detailed views of the galaxy's structure, while space-based telescopes like Hubble have captured breathtaking images that reveal its intricate beauty. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other galaxies. By comparing Andromeda to galaxies at various distances, astronomers can piece together a timeline of cosmic history, tracing the evolution of galaxies from the early universe to the present day. Andromeda's spiral arms, central bulge, and halo are all areas of active research, each offering unique insights into the workings of galaxies. The spiral arms are regions of intense star formation, where massive stars light up the surrounding gas and dust, creating some of the most beautiful and dynamic regions in the galaxy. The central bulge, by contrast, is dominated by older stars, providing a window into the galaxy's past. The halo, with its sparse population of ancient stars and globular clusters, represents the remnants of Andromeda's earliest epochs, a fossil record of the galaxy's formation and growth. As we continue to study Andromeda, we are reminded of the interconnectedness of all things in the universe. The same processes that shape this distant galaxy are at work in the Milky Way and countless other galaxies. By studying Andromeda, we gain a deeper understanding of our own galaxy, our place in the cosmos, and the forces that govern the universe. The Andromeda Galaxy stands as a pillar of scientific curiosity and inquiry, revealing profound truths about the universe's structure and evolution. Each observation, each analysis of this celestial neighbor deepens our understanding of the intricate forces that shape galaxies, including our own Milky Way. Scientists and astronomers have spent decades unraveling its mysteries, from its unique physical characteristics to the secrets hidden in its dark matter halo, which stretches far beyond its visible edges. To expand the horizon of understanding Andromeda, we delve even deeper into the vast scientific details that define this monumental galaxy. One of the key features of Andromeda is its massive dark matter halo, a structure so vast and diffuse that it dominates the dynamics of the galaxy. Observations suggest that this halo extends hundreds of thousands of light-years beyond the galaxy's luminous disk, encompassing both its satellite galaxies and intergalactic space. Unlike the stars and gas within the galaxy, dark matter does not interact with electromagnetic forces, making it invisible to telescopes. However, its gravitational effects are profound. The motion of stars in Andromeda's outer regions can only be explained if we account for the gravitational influence of this unseen mass. The study of Andromeda's dark matter halo has significant implications for cosmology. By measuring its distribution and density, astronomers can test theories about the formation of large-scale structures in the universe. The presence of such a massive halo supports the lambda-CDM, lambda-cold dark matter, model, which posits that galaxies form within vast, invisible scaffolds of dark matter. Furthermore, detailed mapping of Andromeda's halo through gravitational lensing and stellar dynamics provides clues about the nature of dark matter particles, one of the most elusive questions in modern physics. Another remarkable aspect of Andromeda is its double nucleus, a feature that has fascinated scientists since its discovery. This central region contains two distinct clusters of stars, separated by only a few light-years. The prevailing hypothesis is that one of these clusters represents a dense group of stars surrounding Andromeda's supermassive black hole, while the other is a remnant of a smaller galaxy that merged with Andromeda long ago. This unusual configuration offers a unique opportunity to study the dynamics of galactic nuclei and the behavior of stars in extreme gravitational environments. The supermassive black hole at the center of Andromeda is estimated to be about 140 million times the mass of the Sun, significantly larger than the black hole at the center of the Milky Way. This immense gravitational powerhouse shapes the orbits of stars within the galaxy's central bulge and influences the flow of interstellar gas. Observing the interactions between this black hole and its surroundings provides critical data for understanding the growth and evolution of supermassive black holes across the universe. These observations also help astronomers explore the relationship between black holes and their host galaxies, a fundamental question in astrophysics. Andromeda's satellite galaxies add another layer of complexity to its story. These smaller galaxies, such as M32 and M110, orbit Andromeda in intricate patterns, influenced by its massive gravitational pull. Some of these satellites are in the process of being torn apart, their stars and gas streams forming tidal tails that arc across the sky. These interactions offer a glimpse into the hierarchical nature of galaxy formation, where larger systems grow by accreting smaller ones. By studying these satellites and their interactions with Andromeda, scientists can reconstruct the galaxy's merger history, tracing its growth over billions of years. The star-forming regions within Andromeda are particularly noteworthy for their scientific importance. These areas, known as HII regions, are dense clouds of ionized hydrogen where new stars are born. Observations of these regions provide valuable insights into the processes that govern star formation, such as the role of magnetic fields, turbulence, and feedback from massive stars. The distribution and intensity of star-forming regions within Andromeda's spiral arms also shed light on the dynamics of spiral galaxies, revealing how density waves and gravitational interactions shape their structure. Andromeda's globular clusters, ancient spherical collections of stars, are another key area of research. These clusters, which orbit the galaxy in its halo, are among the oldest objects in the universe, with ages exceeding 10 billion years. By studying the chemical composition and motion of these clusters, astronomers can infer the conditions that prevailed in the early universe when Andromeda was forming. Some globular clusters in Andromeda are thought to have originated in smaller galaxies that were later absorbed by the larger system, providing further evidence of its dynamic and turbulent history. One of the most exciting fields of research involving Andromeda is the search for exoplanets within its borders. While detecting planets in another galaxy is extraordinarily challenging, advancements in observational techniques have made this possibility increasingly feasible. For example, gravitational microlensing, a phenomenon where a massive object bends and magnifies the light of a more distant star, can be used to detect planets in Andromeda. If successful, these efforts could reveal the first evidence of planetary systems beyond the Milky Way, offering a new frontier for the study of exoplanets and the potential for life elsewhere in the universe. The impending collision between Andromeda and the Milky Way is one of the most significant events in the galaxy's future. As the two galaxies approach each other, their gravitational interactions will initiate a complex series of events that will reshape both systems. Gas clouds will collide, triggering bursts of star formation that will light up the night sky. Spiral arms will be torn apart, forming tidal streams and bridges of stars. Over billions of years, the two galaxies will merge into a single, massive elliptical galaxy. Simulations of this process provide a detailed look at how such mergers unfold, offering a unique perspective on the long-term evolution of galaxies. The study of Andromeda extends beyond the visible spectrum. Observations in infrared, ultraviolet, and X-ray wavelengths have revealed phenomena that are invisible to the human eye. Infrared studies, for example, penetrate the dust clouds within Andromeda, uncovering regions of intense star formation and the distribution of cooler stars. Ultraviolet observations highlight the youngest and hottest stars, while X-ray studies detect high-energy processes near the galaxy's supermassive black hole and in its dynamic star-forming regions. Together, these observations provide a multi-wavelength view of Andromeda, allowing astronomers to build a comprehensive picture of its structure and activity. Andromeda continues to inspire not only scientists but also the broader public, serving as a symbol of humanity's quest to explore and understand the universe. Its presence in the night sky, visible as a faint smudge to the naked eye, connects us to the vastness of the cosmos and reminds us of our place within it. Through telescopes and spacecraft, we have transformed this distant neighbor from an object of curiosity into a cornerstone of modern astrophysics, a testament to the power of human ingenuity and imagination. The Andromeda Galaxy is more than just a spiral of stars, gas, and dust. It is a dynamic system governed by complex physical processes that stretch the boundaries of our understanding. Each layer of Andromeda, from its luminous core to its diffuse halo, offers a wealth of information about the forces shaping galaxies, the origins of the universe, and the interconnected nature of cosmic structures. To truly appreciate the depth of Andromeda's scientific significance, we must dive further into its intricate details, probing the mechanisms that govern its past, present, and future. One of the most intriguing phenomena in Andromeda is the ongoing interaction between its stars and interstellar medium, ISM. The ISM is a mixture of gas, dust, and plasma that permeates the galaxy, acting as the raw material for star formation. Andromeda's ISM is highly structured, forming filamentary clouds, dense clumps, and expansive regions of ionized gas. Observations of the ISM reveal the complex interplay between gravity, magnetic fields, and feedback from stellar winds and supernovae. These processes regulate the galaxy's star formation rate, determining how efficiently Andromeda converts gas into stars over time. Star formation within Andromeda is not uniform, it is concentrated in specific regions, particularly along the spiral arms. These arms are sites of enhanced density, where shock waves from density waves compress gas clouds, triggering gravitational collapse. The role of density waves in spiral galaxies like Andromeda has been a subject of extensive study, as they provide a framework for understanding the long-lived spiral patterns observed in galaxies. These waves are essentially gravitational oscillations that propagate through the disk of the galaxy, concentrating stars and gas into spiral patterns without the material itself permanently remaining in the arms. This dynamic structure ensures a steady cycle of star formation and dispersal. The star formation process itself is driven by a delicate balance of forces. Gravity works to collapse gas clouds, forming protostars, while thermal pressure, turbulence, and magnetic fields resist collapse. In Andromeda, regions of active star formation are often accompanied by intense feedback from massive stars. These stars emit powerful ultraviolet radiation, which ionizes the surrounding gas, creating glowing nebulae known as HII regions. As these stars reach the end of their lives, they explode as supernovae, releasing vast amounts of energy and enriching the ISM with heavy elements. This enrichment is a critical step in the chemical evolution of galaxies, as it provides the building blocks for planets and life. The chemical composition of Andromeda's stars and ISM offers insights into its history of star formation and mergers. Spectroscopic studies reveal a gradient in metallicity, the abundance of elements heavier than hydrogen and helium, across the galaxy. The central bulge, which contains older stars, has a higher metallicity, reflecting a history of intense star formation in the galaxy's early years. In contrast, the outer regions of the disk and halo have lower metallicity, suggesting a slower rate of chemical enrichment. This gradient is a fingerprint of the processes that have shaped Andromeda over billions of years, from its initial collapse to its interactions with other galaxies. Andromeda's globular clusters are another rich source of information about its chemical and dynamical history. These dense collections of stars are among the oldest objects in the galaxy, with ages often exceeding 10 billion years. By studying the motions and compositions of these clusters, astronomers can reconstruct the conditions that prevailed when Andromeda was forming. Some globular clusters exhibit unusual properties, such as retrograde orbits or distinct chemical signatures, suggesting that they originated in smaller galaxies that were later accreted by Andromeda. These findings support the hierarchical model of galaxy formation, in which large galaxies grow through the assimilation of smaller systems. Beyond its visible components, Andromeda's structure is profoundly influenced by its dark matter halo. This halo, which extends far beyond the galaxy's disk, dominates its mass and shapes the motion of stars and satellite galaxies. By measuring the rotation curve of Andromeda, how the orbital speed of stars varies with distance from the center, astronomers have inferred the presence and distribution of dark matter. The flatness of the rotation curve at large distances, where visible matter becomes sparse, is a clear indication of the gravitational influence of dark matter. This discovery has been pivotal in the development of modern cosmology, highlighting the importance of unseen components in shaping the universe. The relationship between Andromeda and its satellite galaxies is another area of intense study. These smaller systems, such as M32, M110, and others, are bound to Andromeda by its gravitational pull, forming a miniature ecosystem within the local group. Some of these satellites are in the process of being disrupted, their stars forming tidal streams that weave through Andromeda's halo. These streams provide a snapshot of galactic cannibalism in action, illustrating how large galaxies grow by accreting smaller ones. By mapping these streams, astronomers can reconstruct the orbits of the disrupted galaxies, revealing the history of their interactions with Andromeda. The study of Andromeda extends beyond its stars and dark matter to its population of supermassive black holes, neutron stars, and other exotic objects. The central black hole, with a mass of 140 million suns, is a key feature of the galaxy's core. This black hole influences the orbits of nearby stars and may play a role in regulating the flow of gas into the central regions. Observations of X-ray and radio emissions from the core provide clues about the activity of this black hole, which is currently in a relatively quiescent state. Future observations may reveal periods of increased activity, such as flares caused by the accretion of matter. Andromeda's neutron stars and stellar mass black holes are remnants of massive stars that have completed their life cycles. These objects are often found in binary systems, where they accrete matter from a companion star. As this matter falls onto the compact object, it releases energy in the form of X-rays, creating some of the brightest sources in the galaxy. Studying these systems in Andromeda provides insights into the end stages of stellar evolution and the dynamics of binary systems. The future of Andromeda is perhaps its most captivating aspect. Its collision with the Milky Way will mark a new chapter in the history of both galaxies, reshaping their structures and forming a new cosmic entity. Simulations of this merger reveal the complex interplay of gravitational forces, which will tear apart the spiral arms, create tidal bridges and streams, and trigger bursts of star formation. Over billions of years, the two galaxies will settle into a massive elliptical galaxy, a testament to the dynamic and interconnected nature of the cosmos. As we probe deeper into the Andromeda galaxy, it becomes increasingly clear that this celestial neighbor is not just an isolated system but a microcosm of the universe. Its intricate structure, dynamic interactions, and rich history make it a cornerstone of modern astrophysics, offering answers to some of the most profound questions about the nature of galaxies and the forces that govern the cosmos. The Andromeda Galaxy, our closest galactic neighbor, is not just a vast collection of stars, gas, and dark matter, it's a living laboratory where the secrets of the universe are constantly unfolding. Every corner of this colossal spiral galaxy, from its glittering core to its faint outer halo, holds stories of creation, destruction, and rebirth on a scale that challenges the limits of human imagination. At the heart of Andromeda's mysteries lies a component we cannot see, dark matter. This enigmatic substance, which makes up most of the galaxy's mass, doesn't emit light, heat, or any detectable radiation. Instead, we infer its presence through its gravitational influence on the galaxy's stars and gas. Without dark matter, Andromeda's majestic spiral arms wouldn't hold together, they would have unraveled long ago. Dark matter forms a vast, invisible halo around Andromeda, extending hundreds of thousands of light-years beyond its visible disk. The gravity of this halo acts as scaffolding, pulling stars, gas, and dust into the familiar spiral structure we observe today. Mapping this halo is one of the most exciting challenges in astrophysics. Using gravitational lensing, a phenomenon where dark matter bends the light of background objects, astronomers are beginning to trace its contours, revealing a hidden architecture that underpins the galaxy. This work isn't just about understanding Andromeda. Dark matter halos like this exist around all galaxies, and by studying the closest example, we gain insight into the invisible framework that shaped the entire universe. Andromeda's core is unlike anything in the Milky Way. At its center lies not one, but two dense clusters of stars, a double nucleus. One cluster orbits a supermassive black hole that's 140 million times the mass of the Sun. The other, offset slightly, might be the remnants of a smaller galaxy swallowed by Andromeda in the distant past. Why does Andromeda have two nuclei? One hypothesis is that the second cluster is the ghost of a galactic collision. Billions of years ago, Andromeda likely devoured a smaller galaxy, and its core didn't disintegrate entirely, it became trapped, orbiting within Andromeda's gravitational well. Over time, the orbits of these two clusters will likely merge, adding to the already extraordinary mass of the central black hole. Andromeda's spiral arms are bustling regions of activity where stars are born. These arms are shaped by waves of density, essentially gravitational traffic jams. As gas clouds enter these high-density regions, they slow down, compress, and ignite in bursts of star formation. Massive blue stars, some tens of times the mass of the Sun, dominate these regions, shining brightly but living short, fiery lives before exploding as supernovae. These explosions are cosmic recycling events. They scatter heavy elements, like carbon, oxygen, and iron, into the surrounding space, enriching the galaxy's interstellar medium. Without these elements, planets like Earth and life as we know it couldn't exist. In a way, Andromeda's star-forming regions are factories producing the raw materials for future worlds. Beyond its bright core and spiral arms lies Andromeda's halo, a dim, extended region filled with ancient stars and faint remnants of past collisions. This halo is a treasure trove for galactic archaeologists, astronomers who reconstruct the history of galaxies by studying their structures and stellar populations. One of the most fascinating features in Andromeda's halo is its stellar streams, long, faint trails of stars left behind by smaller galaxies that Andromeda has absorbed over billions of years. These streams are cosmic fossils, preserving the memory of galactic mergers. By mapping these trails, astronomers can recreate Andromeda's growth history, revealing a violent past of collisions and cannibalism. The largest and most famous of these streams is the giant stellar stream, a 100,000 light-year-long ribbon of stars thought to be the remains of a once massive satellite galaxy. Studying these structures helps scientists understand not just Andromeda's history, but also how galaxies like the Milky Way grow through mergers and accretion. Perhaps the most dramatic chapter in Andromeda's story is yet to come. Observations show that Andromeda is hurtling toward the Milky Way at a speed of 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide in a cosmic event that will reshape the local group of galaxies forever. What will happen during this collision? As the galaxies approach, their gravitational forces will pull at each other, distorting their shapes and flinging stars into long tidal tails. Gas clouds will collide, sparking bursts of star formation on an unprecedented scale. Over time, the two galaxies will merge into a single, massive elliptical galaxy, often nicknamed Milkomeda. Despite the scale of this event, individual stars are unlikely to collide due to the vast distances between them. Instead, the collision will create a spectacular light show, with new stars igniting and tidal streams painting the night sky. Andromeda's stars likely host countless planets, yet we've only just begun to explore this possibility. Detecting planets in another galaxy is an extraordinary challenge, but emerging techniques like gravitational microlensing are opening new doors. Microlensing occurs when a massive object passes in front of a background star, magnifying its light and revealing the presence of orbiting planets. If planets are found in Andromeda, they could be vastly different from those in the Milky Way, shaped by the unique environment of their galaxy. Some might orbit stars in dense clusters, experiencing a sky filled with thousands of brilliant suns. Others might lie in regions of relative isolation, circling stars on the edges of the galaxy's spiral arms. The discovery of exoplanets in Andromeda would not only expand our understanding of planetary systems but also ignite the imagination, reminding us of the potential for life beyond our galactic borders. The Andromeda Galaxy is more than a cosmic neighbor, it is a gateway to understanding the universe itself. Its proximity allows us to study phenomena that occur in distant galaxies but are too faint to observe in detail. By examining Andromeda's structure, star populations, and interactions, we gain a clearer picture of how galaxies form, evolve, and eventually meet their fate. Andromeda is a living reminder of the interconnectedness of the cosmos. Its stars, much like those in our Milky Way, are born, live, and die in cycles that produce the elements necessary for life. Its dark matter halo, mysterious and invisible, binds it together, just as dark matter structures the universe on the largest scales. As we look toward Andromeda with ever-advancing telescopes and instruments, we are not just observing another galaxy, we are peering into the mechanisms that govern the cosmos itself. And in its vastness, we are reminded of our small but significant place in this grand, unfolding story. The Andromeda Galaxy is a testament to the universe's complexity, a place where science converges with the unknown. Every new observation of its vast expanse reveals another piece of the puzzle about galactic evolution and the forces shaping the cosmos. The galaxy's massive disk contains over 1 trillion stars, a stellar population far larger than that of the Milky Way. Within this stellar population, we find stars in every stage of their life cycle, from bright, young blue stars to ancient red giants that serve as time capsules from an earlier universe. This mixture of stars offers a unique opportunity to study how galaxies grow and change over billions of years. The interplay between stars and their surrounding environment is evident in Andromeda's disk. Its regions of active star formation are lit up by massive, short-lived stars whose intense ultraviolet radiation ionizes nearby gas clouds, creating glowing nebulae. These regions are dynamic, constantly reshaped by the forces of stellar winds and supernova explosions. Such activity enriches the interstellar medium with heavier elements, providing the raw materials for the next generation of stars and planets. Beyond its spiral arms lies a much fainter halo of stars, globular clusters, and streams of debris from past galactic interactions. This halo, extending hundreds of thousands of light-years from the galaxy's center, is a goldmine for understanding Andromeda's violent history. Stellar streams, such as the giant stellar stream, are remnants of smaller galaxies that Andromeda absorbed, a process that continues to this day. These streams are faint and difficult to detect, but their existence provides critical evidence of the hierarchical nature of galaxy formation, where larger systems grow through the accretion of smaller ones. At the core of Andromeda lies its supermassive black hole, surrounded by a dense swarm of stars. This black hole, millions of times the mass of the Sun, is a region of intense gravitational forces. Stars in the vicinity of the black hole exhibit rapid orbital motions, a direct consequence of its immense mass. While currently in a relatively dormant state, this black hole has likely experienced periods of heightened activity, consuming nearby material and releasing enormous amounts of energy. Observing these central regions offers a glimpse into the processes that occur in galactic nuclei, phenomena that are common throughout the universe but challenging to observe in distant galaxies. Andromeda's double nucleus adds another layer of intrigue to its central region. This dual structure, consisting of two closely separated clusters of stars, suggests a complex history of mergers and interactions. One hypothesis is that this feature represents the remnants of a smaller galaxy's core, trapped in Andromeda's gravitational field after a past collision. Such findings illustrate the dynamic and ever-changing nature of galaxies, where interactions with neighbors leave lasting imprints on their structure. As we move outward from the core, the galaxy's spiral arms showcase the intricate patterns formed by density waves. These arms are not static structures but rather regions of increased density that rotate with the galaxy, compressing gas clouds and triggering star formation as they move. The arms' composition, a mix of bright young stars and dark interstellar dust, highlights the ongoing processes that sustain the galaxy's activity. Andromeda's relationship with its satellite galaxies further enriches its story. These smaller companions, such as M32 and M110, orbit within its gravitational influence, and some are being actively disrupted. Tidal forces exerted by Andromeda pull stars and gas from these satellites, adding to the galaxy's mass and leaving behind streams of debris. Observing these interactions helps astronomers understand how galaxies grow over time and how smaller systems contribute to the evolution of larger ones. The dark matter halo surrounding Andromeda is a dominant feature of its structure, extending far beyond its visible components. This halo, made of unseen material, accounts for the majority of the galaxy's mass. Its gravitational influence shapes the orbits of stars and satellite galaxies and plays a crucial role in maintaining the stability of the spiral arms. Mapping the distribution of dark matter in Andromeda provides a critical test for theories about the nature of this mysterious substance and its role in the formation of large-scale cosmic structures. Andromeda's impending collision with the Milky Way is one of the most dramatic events in its future. As the two galaxies approach each other, their mutual gravitational pull will distort their shapes, creating tidal tails and bridges of stars. Gas clouds from both galaxies will collide, igniting bursts of star formation that will illuminate the night skies. Over billions of years, the two systems will merge, forming a massive elliptical galaxy. While such an event might seem catastrophic, the vast distances between individual stars mean that direct collisions are unlikely. Instead, the merger will result in a profound reshaping of both galaxies, a process that has occurred countless times throughout the universe's history. The study of Andromeda extends beyond visible light, with observations across the electromagnetic spectrum providing a more complete picture of its structure and activity. Infrared observations penetrate the dust in its spiral arms, revealing regions of active star formation. Ultraviolet light highlights young, massive stars, while X-ray emissions point to high-energy processes near the supermassive black hole and within binary star systems. Each wavelength reveals a different aspect of the galaxy, contributing to a comprehensive understanding of its nature. Andromeda's role in the local group of galaxies extends beyond its interactions with the Milky Way and its satellites. As the largest galaxy in this group, it exerts a significant gravitational influence, shaping the motions of neighboring galaxies. These interactions provide a scaled-down model of the processes that occur in larger galaxy clusters, where gravitational forces and mergers dominate the dynamics of the system. Studying Andromeda also offers a window into the conditions necessary for the formation of habitable planets and the potential for life beyond the Milky Way. While direct detection of exoplanets in Andromeda is not yet possible, the principles of planetary formation suggest that its stars likely host a diverse array of planets. If life exists elsewhere in the universe, studying nearby galaxies like Andromeda helps us understand the environments where it might thrive. The Andromeda Galaxy, in its immense complexity and dynamic nature, stands as a microcosm of the universe itself. Its stars, gas, dark matter, and interactions with neighboring systems embody the forces that shape galaxies on all scales. As technology advances, our ability to study Andromeda will only deepen, offering new insights into the workings of the cosmos and our place within it. Each discovery within Andromeda's borders reminds us of the intricate and interconnected nature of the universe, a tapestry woven from countless interactions over billions of years. The Andromeda Galaxy's complexity extends into every observable component, providing endless avenues for scientific discovery. Its stars, spanning a wide range of ages and compositions, form the backbone of its luminous structure. By examining the light emitted by these stars, astronomers have gained a detailed understanding of their chemical abundances, ages, and distribution throughout the galaxy. These stellar populations are grouped into distinct categories: the young, massive stars in the spiral arms, the older, metal-rich stars in the bulge, and the ancient, metal-poor stars in the halo. Each group tells a different chapter of Andromeda's history, revealing how the galaxy grew and evolved over cosmic time. The young stars in Andromeda's disk are concentrated in its spiral arms, where conditions are ideal for star formation. These regions are shaped by density waves, which compress gas clouds as they travel through the disk. This compression triggers gravitational collapse, leading to the birth of new stars. Observing these regions allows scientists to study the initial stages of stellar evolution, from protostars to fully formed stars. The intense radiation from young, massive stars heats the surrounding gas, creating ionized bubbles that emit light across the electromagnetic spectrum. The older stars in Andromeda's bulge, by contrast, are remnants of the galaxy's early history. These stars formed during a period of intense star formation that occurred billions of years ago, likely fueled by the inflow of gas from the early universe. The bulge's stars are densely packed, orbiting the galaxy's center in a complex gravitational dance. Their chemical composition reflects the conditions of the early universe, providing a glimpse into the processes that enriched the interstellar medium with heavy elements. Andromeda's halo contains some of the oldest stars in the galaxy, as well as a population of globular clusters that date back to its formation. These clusters, which contain hundreds of thousands of stars, are relics of the early universe, surviving relatively unchanged over billions of years. The motion and composition of these clusters offer clues about Andromeda's formation, suggesting that many of them originated in smaller galaxies that were later absorbed. Studying these ancient structures helps scientists understand the earliest stages of galaxy formation, a process that began less than 1 billion years after the Big Bang. The halo is also home to Andromeda's faintest and most elusive components, its stellar streams. These streams are the remnants of smaller galaxies that Andromeda captured and disrupted through gravitational interactions. By mapping the distribution of these streams, astronomers can reconstruct the galaxy's merger history, revealing a timeline of interactions that shaped its current structure. These streams are not static, they evolve over time, mixing with Andromeda's halo and contributing to its overall mass. Andromeda's dark matter halo, though invisible, is one of its most significant features. This vast, diffuse structure extends far beyond the visible galaxy, accounting for most of its mass. Without the gravitational pull of dark matter, Andromeda's stars and gas would not remain bound, and its spiral structure would not persist. The presence of dark matter is inferred from the galaxy's rotation curve, which remains flat even at great distances from the center. This behavior is inconsistent with the amount of visible matter alone, pointing to the dominance of an unseen component. The nature of dark matter remains one of the greatest mysteries in physics. Observing Andromeda's halo offers a unique opportunity to study this enigmatic substance, as its proximity allows for detailed measurements of its gravitational effects. By combining data from Andromeda with observations of other galaxies and galaxy clusters, scientists hope to constrain the properties of dark matter and understand its role in shaping the universe. Andromeda's relationship with its satellite galaxies adds another layer of complexity to its story. These smaller systems, numbering more than 20, orbit Andromeda within its dark matter halo. Some, like M32 and M110, are easily visible, while others are faint and difficult to detect. These satellites are subject to tidal forces that can strip away their stars and gas, adding to Andromeda's mass and forming tidal streams. The ongoing interactions between Andromeda and its satellites provide a real-time example of hierarchical galaxy formation, a process that has occurred throughout the universe. The impending collision between Andromeda and the Milky Way will mark a transformative event in the local group of galaxies. This merger, set to occur in about 4.5 billion years, will create a new, massive galaxy that combines the stars, gas, and dark matter of both systems. Simulations of this event predict a dramatic reshaping of both galaxies, with their spiral structures destroyed and replaced by a more spheroidal configuration. This process will also redistribute their dark matter halos, creating a new gravitational equilibrium. During the collision, gas clouds from both galaxies will collide and compress, triggering bursts of star formation. These events, known as starbursts, will illuminate the newly forming galaxy, creating regions of intense brightness. At the same time, the supermassive black holes at the centers of Andromeda and the Milky Way may merge, releasing enormous amounts of energy in the form of gravitational waves. These waves, ripples in spacetime, will propagate outward, carrying information about the black hole's masses and spin. While the Andromeda-Milky Way collision is often described as a cataclysmic event, the vast distances between stars mean that direct stellar collisions are unlikely. Instead, the merger will reshape the orbits of stars and gas, creating new tidal structures and redistributing material throughout the galaxy. Over billions of years, the two galaxies will settle into a stable configuration, forming an elliptical galaxy that astronomers have dubbed Milkomeda. The study of Andromeda extends across the electromagnetic spectrum, with observations in ultraviolet, infrared, and X-ray wavelengths providing a more complete picture of its structure and activity. Ultraviolet light reveals the youngest, hottest stars in the galaxy, while infrared observations penetrate dust clouds to uncover regions of active star formation. X-ray emissions, on the other hand, highlight high-energy processes near Andromeda's supermassive black hole and within its population of neutron stars and stellar mass black holes. The wealth of data collected from Andromeda has implications far beyond the local group. By studying its structure, dynamics, and composition, astronomers can test theories of galaxy formation and evolution that apply across the universe. Andromeda serves as a laboratory for understanding the processes that govern galaxies at all scales, from the smallest dwarfs to the largest clusters. The Andromeda Galaxy, in its vastness and complexity, embodies the interconnected nature of the universe. Each of its components, from the stars in its disk to the dark matter in its halo, plays a role in shaping its structure and behavior. As our understanding of Andromeda deepens, so too does our appreciation for the forces that govern the cosmos. It stands as a reminder of the universe's boundless potential for discovery, a cosmic neighbor whose secrets continue to inspire and challenge our understanding of the universe. The Andromeda Galaxy is not merely a subject of awe-inspiring beauty, it is a cornerstone of astrophysical research, a galaxy so close that it offers a detailed view into processes that govern the universe at large. With every new generation of instruments and theoretical models, Andromeda becomes an even more potent laboratory for exploring the physics of galaxies, the nature of dark matter, and the history of the cosmos. A significant aspect of ongoing research into Andromeda involves its rotational dynamics. The galaxy's rotation curve, a plot showing how the orbital velocity of stars changes with distance from the center, provides one of the most compelling pieces of evidence for the existence of dark matter. Unlike what would be expected if only visible matter were present, the rotation curve of Andromeda remains nearly flat at large distances from its core, even where the visible mass is negligible. This indicates the presence of an unseen halo of dark matter extending far beyond the luminous disk. By comparing the rotation curves of Andromeda with those of other galaxies, astronomers can refine models of dark matter distribution and its influence on galactic structure. In addition to dark matter, studies of Andromeda's stellar populations are unlocking secrets about galaxy formation and evolution. Detailed spectroscopic surveys, such as those conducted with the Keck Observatory and the Hubble Space Telescope, have allowed scientists to determine the metallicity of stars in different regions of the galaxy. Metallicity, the proportion of elements heavier than hydrogen and helium, acts as a cosmic clock, revealing the star formation history of the galaxy. The high metallicity of stars in Andromeda's central bulge reflects an early period of rapid star formation, likely driven by the inflow of gas and the intense gravitational dynamics of its core. In contrast, the outer regions of the disk and halo contain stars with lower metallicities, indicating slower chemical enrichment over time. These metallicity gradients are critical for understanding not only Andromeda but also galaxy evolution on a universal scale. For instance, the presence of metal-poor stars in Andromeda's halo suggests that these stars are remnants of smaller galaxies that merged with Andromeda in the past. This supports the hierarchical model of galaxy formation, in which large galaxies grow through the accretion of smaller ones. By studying the ages, compositions, and motions of these stars, astronomers can reconstruct the timeline of Andromeda's mergers and interactions, painting a picture of its growth over billions of years. One of the most fascinating discoveries in recent years has been the identification of tidal streams in Andromeda's halo. These faint, elongated structures are the remnants of dwarf galaxies torn apart by Andromeda's gravitational pull. Among the most prominent is the giant stellar stream, a structure spanning over 100,000 light-years, thought to be the remains of a galaxy that collided with Andromeda about 2 billion years ago. By mapping these streams with high-precision instruments, such as the Gaia Space Observatory, scientists can probe the gravitational potential of Andromeda's halo, providing insights into the distribution of dark matter and the galaxy's dynamic history. Beyond its stars and dark matter, Andromeda's interstellar medium, ISM, is a subject of intense study. The ISM, consisting of gas, dust, and cosmic rays, plays a crucial role in the life cycle of galaxies by serving as the reservoir for star formation. Observations in multiple wavelengths, including radio, infrared, and submillimeter, have revealed complex structures within Andromeda's ISM, from dense molecular clouds to diffuse atomic hydrogen regions. These structures are shaped by the interplay of gravitational forces, turbulence, magnetic fields, and feedback from massive stars and supernovae. The role of magnetic fields in shaping Andromeda's ISM is an emerging area of research. Using instruments such as the Very Large Array and the Atacama Large Millimeter/Submillimeter Array, astronomers are mapping the galaxy's magnetic field structure. These fields influence the motion of charged particles in the ISM, affecting star formation and the dynamics of gas flows. Understanding the strength and orientation of magnetic fields in Andromeda provides a deeper understanding of how galaxies regulate star formation and maintain their structure over time. Andromeda's satellite galaxies add another layer of complexity to its ecosystem. With over 20 known satellites, Andromeda serves as a microcosm for studying the dynamics of galaxy groups. Some satellites, like M32, show evidence of tidal stripping, where gravitational interactions with Andromeda have removed stars and gas, leaving behind a compact remnant. Others, like M110, are actively interacting with Andromeda, contributing material to its halo. These interactions provide a living example of galaxy evolution in action, offering a detailed view of processes that occur across the universe. The future merger between Andromeda and the Milky Way is one of the most anticipated cosmic events in the local universe. Current simulations of this event, such as those conducted with supercomputers using the Illustris and Eagle cosmological models, predict a series of dramatic transformations. As the galaxies approach, their gravitational interactions will distort their shapes, creating tidal tails and bridges of stars and gas. These features, reminiscent of structures seen in interacting galaxies like the antennae galaxies, provide a preview of what might unfold. The collision will ignite bursts of star formation, driven by the compression of gas as the galaxies merge. Over time, their central black holes will coalesce, emitting gravitational waves detectable by next-generation observatories such as the Laser Interferometer Space Antenna, LISA. Even as we anticipate this distant future, Andromeda remains a critical subject for understanding galaxy clusters beyond the local group. Its role as the largest member of our local group offers a scaled-down model of the processes occurring in massive galaxy clusters, where interactions between dark matter halos, gas dynamics, and star formation play out on a grander scale. By studying Andromeda, scientists refine the tools and theories that apply to systems billions of light-years away. Andromeda's study is also pushing the boundaries of exoplanet science. While detecting planets in another galaxy remains a challenge, methods such as gravitational microlensing and spectroscopy hold promise for identifying planets within Andromeda. Detecting such planets would open a new frontier in the search for extraterrestrial life, providing the first opportunity to study worlds beyond the Milky Way. If Andromeda's planetary systems resemble those of the Milky Way, it is likely teeming with diverse planets, some potentially orbiting within habitable zones where conditions might support life. As new telescopes come online, including the Extremely Large Telescope and the James Webb Space Telescope, Andromeda's secrets will continue to be unveiled. These instruments will provide unparalleled resolution and sensitivity, allowing astronomers to study individual stars and planetary systems within Andromeda, as well as its faintest tidal streams and most diffuse dark matter structures. Andromeda, as a living archive of cosmic history, will remain a focal point for unraveling the universe's grandest mysteries, inspiring generations of researchers and dreamers alike. The Andromeda Galaxy, as a living archive of cosmic evolution, continues to captivate the scientific community. With its immense size and proximity, it serves as an unparalleled laboratory for testing theories of galactic dynamics, star formation, and the nature of dark matter. As observational tools improve, researchers uncover increasingly intricate details about the processes that shape this massive spiral galaxy and its surrounding environment. One of the most active areas of research focuses on the interplay between Andromeda's interstellar medium, ISM, and star formation. The ISM is not a uniform structure, it consists of diverse phases, from cold molecular clouds to hot, ionized regions. Molecular clouds, composed primarily of molecular hydrogen, H2, are the birthplace of stars. Observations using radio telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, reveal these dense clouds in extraordinary detail. By studying their composition, density, and temperature, scientists gain insights into the conditions that lead to star formation. In Andromeda, these clouds are predominantly located along its spiral arms, where the compression of gas by density waves provides the necessary triggers for gravitational collapse. The role of feedback mechanisms in regulating star formation is another critical aspect of Andromeda's evolution. Massive stars, once formed, exert powerful feedback on their surroundings through stellar winds, ultraviolet radiation, and, ultimately, supernova explosions. These feedback processes inject energy into the ISM, heating it and dispersing gas, which can either suppress or stimulate further star formation. In Andromeda, feedback-driven bubbles and shells of ionized gas are visible throughout its disk, offering a dynamic view of the cyclical nature of star formation. Andromeda's spiral arms, while appearing as fixed features, are in constant motion. They are formed and sustained by density waves, which propagate through the galactic disk, concentrating stars and gas into patterns that resemble a spiral. These waves are not made of physical material but are rather regions of higher gravitational density that travel through the galaxy. Observing these arms in Andromeda has helped refine our understanding of how such structures form and persist in spiral galaxies across the universe. The distribution of stars and gas within these arms also provides clues about the interplay between galactic rotation, gravity, and star formation. The central bulge of Andromeda presents a stark contrast to its active spiral arms. This region, dominated by older, redder stars, is relatively quiescent, with little ongoing star formation. The stars in the bulge orbit in complex patterns, influenced by the galaxy's supermassive black hole and the dense gravitational environment of the central region. By studying the motion of these stars using spectroscopy, astronomers can map the distribution of mass in the bulge, including the unseen mass of the black hole and dark matter. These studies reveal that Andromeda's supermassive black hole, with a mass of approximately 140 million suns, is significantly larger than the one at the center of the Milky Way, suggesting differences in the growth histories of the two galaxies. The double nucleus of Andromeda, a rare and fascinating feature, continues to be a subject of intense investigation. Detailed observations suggest that this structure may result from the accretion of a smaller galaxy, whose core became embedded in Andromeda's central region. This scenario is supported by the presence of distinct stellar populations within the double nucleus, indicating different origins. This finding highlights the dynamic and often violent history of galaxy interactions and mergers that have shaped Andromeda into its current form. Andromeda's extensive halo, stretching far beyond its visible disk, is another area rich with scientific interest. This halo contains a mix of stars, globular clusters, and streams of debris from past mergers. Observations using the Hubble Space Telescope have revealed that Andromeda's halo is significantly more massive and extended than previously thought, providing crucial data about the distribution of dark matter. The halo also contains metal-poor stars, some of the oldest in the galaxy, which are remnants from the earliest phases of galactic formation. These stars serve as fossils, preserving information about the conditions in the universe when Andromeda was just beginning to form. The satellite galaxies of Andromeda, including M32, M110, and dozens of smaller dwarf galaxies, form a dynamic and interactive system. Some of these satellites are in the process of being disrupted by Andromeda's tidal forces, adding to the streams of stars in its halo. Others appear to be relatively stable, orbiting at distances where tidal forces are weaker. These satellites provide a microcosm for studying the hierarchical formation of galaxies, showing how smaller systems are absorbed by larger ones over time. They also serve as laboratories for understanding the role of dark matter in shaping the dynamics of small galaxies, as their visible mass is often insufficient to account for their observed motions. The impending collision between Andromeda and the Milky Way, while billions of years in the future, continues to be a focal point of theoretical studies and simulations. By modeling this event using powerful supercomputers, astronomers can predict the stages of the merger, from the initial gravitational interactions to the eventual formation of a single elliptical galaxy. These simulations incorporate data about the mass, composition, and motion of both galaxies, as well as their dark matter halos, to create highly detailed scenarios. The results provide insights not only into the future of our local group but also into the broader processes of galaxy evolution in the universe. In addition to its relevance for understanding large-scale cosmic structures, Andromeda is increasingly becoming a target for studies of exoplanetary systems. While direct detection of exoplanets in Andromeda remains beyond current technology, the principles of planetary formation suggest that many of its stars are likely to host planets. Observations of star-forming regions in Andromeda reveal conditions similar to those in the Milky Way, where planets are known to form around stars of various types. Future advancements in observational techniques, such as high-resolution spectroscopy and microlensing surveys, may allow astronomers to detect exoplanets within Andromeda, opening a new frontier in the search for habitable worlds beyond our galaxy. Andromeda's role as the largest galaxy in the local group also provides a unique perspective on the dynamics of galaxy clusters. Its interactions with the Milky Way and other members of the local group offer a scaled-down model of the processes that occur in much larger galaxy clusters, where gravitational forces and collisions dominate. By studying Andromeda, astronomers can test theories of cluster evolution, including the influence of dark energy on the expansion of the universe. Every aspect of Andromeda, from its smallest star-forming regions to its vast dark matter halo, contributes to our understanding of the universe. It is not merely a distant object in the sky but a dynamic, evolving system that embodies the processes shaping galaxies everywhere. As technology advances and observational techniques improve, Andromeda will continue to serve as a cornerstone of astrophysical research, inspiring new discoveries and expanding our knowledge of the cosmos. The Andromeda Galaxy continues to captivate not only astronomers but also the general public due to its role as both a scientific treasure trove and a cosmic marvel. Beyond its already well-documented features, there are countless other intriguing facets that expand our understanding of the universe and provoke even deeper questions about its nature. One particularly fascinating aspect of Andromeda is the ongoing discovery of ultra-diffuse galaxies, UDGs, within its vicinity. These faint, ghostly systems, scattered around Andromeda, are incredibly low in luminosity relative to their size. UDGs challenge our understanding of galaxy formation, as they are thought to contain large amounts of dark matter while having very few stars. Their existence raises questions about how galaxies form and survive in such extreme conditions. Observing these faint galaxies around Andromeda helps astronomers test models of dark matter and study how gravitational interactions with larger systems affect small, diffuse galaxies. Another intriguing topic is Andromeda's stellar remnants, white dwarfs, neutron stars, and black holes. These objects represent the end stages of stellar evolution and are crucial for understanding the life cycles of stars in Andromeda. By observing the X-rays emitted by binary systems where a neutron star or black hole accretes material from a companion star, astronomers can measure the mass, spin, and other properties of these exotic remnants. Such observations also provide clues about the population of high-mass stars that existed in Andromeda's past, as these stars eventually evolve into compact objects. The search for intermediate-mass black holes, IMBHs, within Andromeda is an area of growing interest. IMBHs are thought to represent a missing link in the black hole population, bridging the gap between stellar mass black holes and supermassive black holes. Evidence for these elusive objects could come from dense star clusters in Andromeda's halo or from X-ray sources that exhibit peculiar properties. If confirmed, IMBHs could help explain how supermassive black holes like the one at Andromeda's center grow over time. The outer edges of Andromeda's disk and halo also hold surprises, such as extended ultraviolet (UV) disks discovered by the Galaxy Evolution Explorer (GALEX). These UV features suggest ongoing star formation in regions far beyond the visible disk of the galaxy. Such discoveries challenge traditional notions of where and how star formation occurs in spiral galaxies, hinting at the presence of low-density gas reservoirs that may slowly contribute to the galaxy's growth over billions of years. A lesser-discussed yet intriguing feature of Andromeda is its magnetic field. Magnetic fields are notoriously difficult to study, but they play a critical role in shaping the behavior of galaxies by influencing the motion of charged particles and the dynamics of the interstellar medium. Recent observations suggest that Andromeda's magnetic field is well-ordered, extending across its spiral arms and potentially contributing to the formation of dense molecular clouds. By mapping this magnetic field, scientists are beginning to uncover its role in regulating star formation and driving the flow of gas within the galaxy. In the realm of theoretical physics, Andromeda also provides a unique opportunity to test alternative theories of gravity. The behavior of stars in its halo, for instance, can be used to test modified Newtonian dynamics, MOND, or other theories that aim to explain galactic rotation curves without invoking dark matter. While dark matter remains the most widely accepted explanation, galaxies like Andromeda serve as critical testing grounds for alternative models, ensuring that our understanding of fundamental physics remains robust and open to new ideas. Andromeda's role in cosmology extends to its position within the local group, which itself is a microcosm of the larger cosmic web. The local group is dominated by Andromeda and the Milky Way, but it also includes smaller galaxies like the Triangulum Galaxy, M33, and numerous dwarfs. By studying the motion of these galaxies relative to Andromeda, astronomers gain insights into the gravitational interactions within galaxy groups. These interactions, in turn, reflect the distribution of dark matter on larger scales, helping to constrain cosmological models that describe the evolution of the universe from the Big Bang to the present day. On a more speculative note, Andromeda's potential for hosting habitable environments is a topic that sparks the imagination. While exoplanet research within the Milky Way has revealed thousands of planets, extending these studies to Andromeda could open new frontiers. Advanced methods, such as transit photometry or gravitational microlensing applied on an intergalactic scale, may one day allow the detection of planets orbiting stars in Andromeda. If such planets are found, their diversity could provide a broader context for understanding the conditions necessary for life. Furthermore, the discovery of biosignatures, chemical markers that indicate the presence of life, on planets in Andromeda would redefine humanity's place in the cosmos. The exploration of Andromeda is also fueling technological advancements. Instruments capable of resolving individual stars in Andromeda, such as those aboard the Hubble Space Telescope or the upcoming Extremely Large Telescope, ELT, push the boundaries of optical engineering. Similarly, the computational power required to simulate the future collision between Andromeda and the Milky Way drives innovation in numerical modeling and high-performance computing. These technologies not only deepen our understanding of Andromeda but also have broader applications in fields ranging from artificial intelligence to climate modeling. As humanity's knowledge of Andromeda grows, so does our appreciation of its role as a cornerstone of modern astrophysics. It is a galaxy that embodies the complexity, dynamism, and interconnectedness of the universe. Each new discovery, whether it involves the behavior of stars, the distribution of dark matter, or the interactions of satellite galaxies, adds to our understanding of the cosmos and our place within it. Andromeda stands as a symbol of both the mysteries that remain and the relentless pursuit of knowledge that defines humanity's exploration of the universe. The Andromeda Galaxy, vast and enigmatic, represents a bridge between the known and the unknown, between the observable universe and the mysteries that lie beyond. Its proximity provides humanity with an unparalleled opportunity to study a galaxy in extraordinary detail, serving as both a mirror and a map for understanding galaxies across the cosmos. Each star, each tidal stream, and each faint trace of dark matter within Andromeda tells a story, not just of its own formation, but of the fundamental processes that govern the universe. As we continue to probe Andromeda's secrets, we are reminded of the immense scale of the cosmos and our relatively small yet significant place within it. This galaxy, with its trillion stars and complex dynamics, invites us to think not only about the mechanisms that shape galaxies but also about the nature of existence itself. Its eventual collision with the Milky Way, an event of unimaginable scale, emphasizes the ever-changing, interconnected nature of the universe, where no galaxy exists in isolation. Andromeda is more than a neighbor, it is a cosmic partner in our journey of discovery. As our technology advances and our curiosity deepens, this majestic galaxy will continue to inspire not only scientific inquiry but also a profound sense of wonder. Through Andromeda, we glimpse the infinite possibilities of the cosmos, and in that glimpse, we find both questions to pursue and answers that redefine our understanding of the universe. It stands as a testament to the unending dance of matter, energy, and time, a galaxy that invites us to explore, imagine, and reach beyond. Galaxies are the grand architectural masterpieces of the universe, vast cosmic cities comprising billions or even trillions of stars, planets, nebulae, dark matter, and supermassive black holes. These celestial structures, ranging in shape from majestic spirals to enigmatic ellipticals and irregular clusters, have captivated humanity for centuries, igniting an insatiable curiosity about their origin, evolution, and destiny. Among them, the Sombrero Galaxy, or Messier 104, stands as one of the most striking and mysterious examples, a galactic enigma revealing the universe's complexity and grandeur. The Sombrero Galaxy, located approximately 31 million light-years from Earth in the Virgo constellation, earned its name due to its distinctive appearance. When viewed through telescopes, it resembles a wide-brimmed sombrero hat, thanks to its bright central bulge surrounded by a dark, sharply defined dust lane. This iconic structure represents a hybrid of galactic types, combining features of spiral and elliptical galaxies. The luminous core and large halo of globular clusters suggest an elliptical nature, while the prominent disk and dust lane highlight its spiral characteristics. This duality challenges traditional classification systems and invites deeper investigation into the processes that shape galaxies. Astronomical studies suggest that the Sombrero Galaxy is a massive object, containing roughly 800 billion solar masses. Its halo is populated by an exceptional number of globular clusters, up to 2,000, far surpassing the few hundred typically found in a galaxy like the Milky Way. This abundance raises questions about the galaxy's history and whether it formed through a series of mergers or evolved in isolation. Additionally, the Sombrero galaxy's core harbors a supermassive black hole with a mass of about 1 billion times that of our Sun, further accentuating its role as a cosmic powerhouse. Modern astronomy relies on a combination of observational techniques and theoretical modeling to study galaxies like M104. Optical telescopes, such as the Hubble Space Telescope, provide high-resolution images, capturing the intricate details of the galaxy's structure. Meanwhile, radio telescopes delve into the cold, diffuse gas that fuels star formation, and X-ray observatories detect emissions from the hot gas swirling around its central black hole. Spectroscopy, a technique that analyzes the light spectrum emitted or absorbed by a galaxy, reveals crucial information about its chemical composition, motion, and distance. One of the most intriguing aspects of galactic research involves uncovering the role of dark matter. Observations of galaxies, including the Sombrero galaxy, suggest that their visible mass, stars, gas, and dust, is insufficient to account for the gravitational forces required to maintain their structure. Instead, an invisible, enigmatic substance known as dark matter provides the necessary mass to hold these cosmic entities together. Studies indicate that up to 90% of a galaxy's total mass may be dark matter, yet its nature remains one of the greatest mysteries in astrophysics. The study of galaxies is not merely a pursuit of academic curiosity. It holds profound implications for understanding the universe's past and future. Galaxies are the fundamental building blocks of the cosmos, and their evolution is intricately linked to the history of the universe itself. The light we see from distant galaxies travels vast distances, allowing astronomers to peer billions of years into the past. By studying these ancient light sources, we reconstruct the timeline of the universe, from the Big Bang to the present day. The Sombrero galaxy, with its unusual characteristics, provides a unique laboratory for exploring these cosmic questions. Its bright core offers a window into the behavior of supermassive black holes and their influence on surrounding stars and gas. The dust lane, meanwhile, serves as a site of active star formation, illustrating the cyclical nature of galactic evolution. Moreover, the halo's globular clusters may contain some of the oldest stars in the universe, offering insights into the early stages of galaxy formation. In recent years, advancements in technology have revolutionized our ability to study galaxies. Ground-based observatories equipped with adaptive optics can correct for the blurring effects of Earth's atmosphere, achieving near-space-level clarity. Space-based instruments, such as the James Webb Space Telescope, extend our reach into infrared wavelengths, penetrating the dust and gas that obscure visible light. These tools enable astronomers to study galaxies across the electromagnetic spectrum, uncovering hidden structures and processes. The exploration of galaxies also intersects with other scientific disciplines, such as cosmology and particle physics. The distribution and behavior of galaxies provide critical evidence for understanding dark energy, the mysterious force driving the universe's accelerated expansion. Observations of galactic clusters, the largest gravitationally bound structures, test theories about the nature of gravity and the large-scale structure of the cosmos. Despite these advancements, many questions remain unanswered. How do galaxies form and evolve over billions of years? What triggers the transition from active star formation to quiescence? How do interactions and mergers shape their structure? The Sombrero galaxy exemplifies these mysteries, as its hybrid nature hints at a complex and perhaps turbulent past. Furthermore, the study of galaxies holds profound philosophical and existential implications. By examining these distant worlds, we confront our place in the universe. Galaxies are not static monuments but dynamic ecosystems, constantly evolving and interacting. They remind us that the universe is a vast, interconnected web of matter and energy, governed by the same physical laws that shape our own existence. In the coming decades, the quest to unravel the mysteries of galaxies will continue to drive innovation and discovery. Next-generation telescopes, such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA), promise to expand our understanding of the cosmos. These instruments will provide unprecedented resolution and sensitivity, enabling detailed studies of galaxies across cosmic time. As we gaze at the Sombrero Galaxy and its brethren, we are not merely observing distant objects. We are engaging in a profound dialogue with the universe, seeking to understand the forces that shape it and our place within it. The study of galaxies is a testament to human curiosity and ingenuity, a pursuit that transcends borders and generations, uniting us in a shared quest for knowledge and wonder. This extensive and enriched narrative captures the essence of galactic science and highlights the Sombrero Galaxy's allure and significance. Let me know if you'd like further elaboration or a specific focus on any aspect. The Sombrero Galaxy, often regarded as one of the most beautiful galaxies in the universe, is not merely an object of aesthetic fascination. It holds within it profound scientific puzzles that challenge our understanding of cosmic evolution. Imagine standing on the edge of its luminous disk, where the gravitational pull of billions of stars dances with the unseen forces of dark matter, shaping the intricate ballet of its structure. Every pinpoint of light in this galaxy represents a solar system, a potential cradle of life, and a glimpse into the vast possibilities of existence. What makes M104 particularly intriguing is the stark contrast between its bright, tightly packed central bulge and the thin, flat disk encircling it. This juxtaposition raises questions about its formation. Did it evolve in isolation, quietly accumulating mass over billions of years? Or did it endure violent encounters with other galaxies, merging and absorbing them into its structure? Theories abound, but definitive answers remain elusive, veiled behind the enigmatic glow of its stars and the cold embrace of interstellar dust. The supermassive black hole at the heart of the Sombrero Galaxy is another captivating feature. Black holes are the ultimate cosmic enigmas, regions where gravity is so intense that not even light can escape. In the case of M104, this black hole is estimated to be over 1 billion times the mass of our Sun, exerting a profound influence on its surroundings. The swirling disk of gas and dust feeding this gravitational monster emits high-energy X-rays, providing a rare glimpse into the violent processes occurring at galactic cores. These observations allow scientists to probe the relationship between black holes and the galaxies that host them, a relationship that remains one of the most profound mysteries in astrophysics. Zooming out, the halo of the Sombrero Galaxy reveals another layer of its story. This diffuse, spherical region is home to thousands of globular clusters, dense collections of ancient stars bound tightly by gravity. Each of these clusters is like a relic from the early universe, a fossilized record of the conditions that existed shortly after the Big Bang. Studying these clusters offers clues about the galaxy's formation history and the broader processes that shaped the cosmos in its infancy. Perhaps one of the most mind-bending aspects of studying galaxies like the Sombrero is the realization that we are looking into the past. The light from M104 takes 31 million years to reach us, meaning we see it not as it is today, but as it was when dinosaurs roamed the Earth. This concept, known as look-back time, transforms galaxies into time machines, allowing us to observe the universe's history unfolding before our eyes. Galaxies are not isolated islands floating in space. They are interconnected through vast cosmic structures, forming clusters, superclusters, and filaments that span millions of light-years. The Sombrero galaxy resides near the Virgo cluster, one of the most massive galaxy clusters in the local universe. This cluster's gravitational influence, along with the mysterious push of dark energy, subtly shapes M104's trajectory. The interplay of these forces is a microcosm of the larger cosmic drama, where gravity and dark energy compete to define the universe's fate. Dark energy itself is a tantalizing concept, one that emerged from the study of galaxies. In the 1990s, astronomers discovered that the universe is not just expanding, it is accelerating. This revelation, awarded the Nobel Prize in Physics in 2011, suggests the presence of a mysterious force permeating space. Galaxies, as the visible markers of the universe's expansion, are key to unraveling this mystery. Observing how galaxies like the Sombrero move and evolve provides critical data for understanding the nature of dark energy and its implications for the ultimate destiny of the cosmos. But even as we look outward, the study of galaxies reflects back on us, forcing us to confront profound questions about our own existence. What role does Earth play in this vast cosmic tapestry? Are we an anomaly, a unique phenomenon in a universe dominated by lifeless gas and dust? Or are galaxies teeming with planets like ours, harboring lifeforms gazing back at the cosmos, wondering about their place just as we do? The Sombrero galaxy, with its serene beauty and hidden complexities, invites us to ponder these questions. It beckons us to explore not just its physical structure, but the deeper truths it holds about the universe and ourselves. Every photon of light from its stars carries a story, a tale of creation, transformation, and endless possibility. And as our telescopes grow more powerful, as our understanding deepens, we edge closer to deciphering these tales, one galaxy at a time. The journey to uncover the secrets of galaxies like M104 is far from over. The universe is a living, breathing entity, constantly evolving and reshaping itself. The Sombrero galaxy, though seemingly static in the cold depths of space, is part of this grand cosmic symphony, a symphony we are only beginning to understand. The more we learn, the more we realize how much remains unknown, how much wonder lies ahead. And so, we continue to look up, to question, to dream, knowing that each discovery is not an endpoint, but a new beginning. As we dive deeper into the mysteries of the Sombrero galaxy and its kind, the questions only become more compelling. Why does this galaxy, with its serene, symmetrical structure, hold such an unusually large supermassive black hole? Could this central colossus be the key to understanding the galaxy's past? Black holes are often associated with chaos and destruction, yet in the case of the Sombrero galaxy, it appears to contribute to a striking balance, a paradox that defies our expectations. The supermassive black hole at the core of M104 is not just a gravitational anomaly but a cosmic engine. Its immense mass allows it to control the surrounding gas, dust, and even entire stars. This process creates an accretion disk, an extraordinarily hot and bright structure formed as matter spirals into the black hole. The energy radiated by this disk is so intense that it can outshine the combined light of millions of stars. What's fascinating is how this energy can also regulate star formation, either by compressing gas clouds to trigger new stars or by blasting the surrounding area with radiation, suppressing stellar birth entirely. Understanding this delicate balance is essential for piecing together how galaxies evolve over time. The Sombrero galaxy also serves as a cosmic time capsule. Its bright halo, filled with globular clusters, holds the secrets of the early universe. These clusters are some of the oldest known structures in the cosmos, containing stars that formed when the universe was still young and dominated by primordial elements like hydrogen and helium. By analyzing the light from these ancient stars, astronomers can decode the chemical fingerprints left behind, revealing when and where they were formed. This helps scientists reconstruct not only the history of M104 but also the broader story of galaxy formation. However, the Sombrero galaxy is not just a relic of the past, it is an active participant in the present-day cosmic web. Galaxies are not solitary wanderers, they are part of vast, interconnected structures that stretch across the universe. The Virgo supercluster, where M104 resides, is a massive node in this web, connecting filaments of dark matter, gas, and galaxies. Dark matter, although invisible, plays a crucial role in this network. It provides the gravitational scaffolding that holds galaxies together and binds them into clusters. Without dark matter, the Sombrero galaxy, along with every other galaxy, would simply fly apart. The quest to understand dark matter has led to some of the most ambitious experiments in physics. From underground detectors buried deep within mountains to particle accelerators like the Large Hadron Collider, scientists are hunting for elusive particles that could explain this unseen force. The Sombrero galaxy's rotation curve, how its stars move at different distances from the center, offers compelling evidence for dark matter's presence. Unlike what Newtonian physics predicts, the outer stars in M104 rotate at speeds that suggest the galaxy is surrounded by a massive, invisible halo of dark matter. The Sombrero galaxy also offers a lens into the future of our own Milky Way. In billions of years, the Milky Way and the Andromeda galaxy are expected to collide, forming a new galactic entity. While such mergers may seem chaotic, they are part of the natural life cycle of galaxies. The Sombrero's peculiar structure, its bright core and extended halo, may be the result of a similar ancient merger, preserved in its serene appearance. By studying galaxies like M104, astronomers can predict the potential outcomes of such cosmic collisions, providing a glimpse into the distant future. Another captivating aspect of M104 is its star-forming regions, hidden within its dusty disk. Despite its old, massive halo, the Sombrero galaxy continues to produce new stars, a testament to the dynamic processes within its structure. Star formation is not a uniform process, it requires the right conditions, a delicate interplay of gravity, temperature, and gas density. The dark dust lanes of M104, sharply etched against its luminous core, are the nurseries where these stars are born. Observing these regions in detail using infrared telescopes allows scientists to study how stars form under varying conditions, deepening our understanding of this universal phenomenon. And yet, for all its beauty and secrets, the Sombrero galaxy reminds us of the vastness of the unknown. Its sheer scale, spanning 50,000 light-years, challenges our ability to comprehend the immensity of the universe. Within this single galaxy lie billions of stars, each potentially surrounded by planets, some of which may harbor the conditions for life. The search for extraterrestrial life is one of humanity's most profound endeavors, and galaxies like M104 provide countless opportunities for discovery. If intelligent civilizations exist elsewhere, they may also gaze upon their version of the Sombrero galaxy, pondering their place in the cosmos as we do. The study of galaxies, including M104, is a multidisciplinary effort. Astronomers, physicists, chemists, and even biologists collaborate to unravel the complex tapestry of the universe. Instruments like the James Webb Space Telescope, JWST, have revolutionized our ability to study galaxies in unprecedented detail. With its infrared capabilities, the JWST can peer through the dust and reveal the hidden layers of the Sombrero galaxy, uncovering new insights into its star-forming regions and central black hole. What's perhaps most thrilling is that every new discovery about galaxies like M104 opens the door to even deeper mysteries. Why do some galaxies stop forming stars while others remain active? What role do magnetic fields play in shaping their structure? And how does the interplay between dark matter and baryonic matter influence their evolution? The Sombrero galaxy, with its iconic beauty and scientific complexity, is more than just a distant object in the night sky. It is a testament to the universe's creativity and the unyielding curiosity of humankind. It is a reminder that even as we uncover the secrets of the cosmos, the universe always keeps something more to reveal, an endless source of wonder and inspiration. And so, we look up, not just to observe, but to dream, to question, and to discover our place in this vast and astonishing cosmos. The Sombrero galaxy is not merely a dazzling object suspended in the vast darkness of space, it is a cosmic laboratory where the laws of physics, chemistry, and cosmology converge, challenging the boundaries of human understanding. Its unique features provide an opportunity to explore some of the universe's most profound mysteries, from the nature of dark matter to the origins of supermassive black holes and even the potential for life in distant worlds. One of the most perplexing questions about galaxies like the Sombrero is the role of dark matter, the unseen mass that outweighs visible matter by a factor of about 5 to 1. Without dark matter, the rapid rotation speeds of stars in M104's outer regions would cause them to be flung into intergalactic space. Yet, they remain bound to the galaxy, circling the core as though held by an invisible hand. This phenomenon, first observed in the 20th century, was one of the key pieces of evidence for the existence of dark matter. But what is it? Is it made of exotic particles yet to be discovered? Or could it represent a flaw in our understanding of gravity itself? To explore these questions, scientists use powerful simulations. Supercomputers recreate the Sombrero galaxy, incorporating the known laws of physics and different hypotheses about dark matter. These simulations are not mere theoretical exercises, they are predictive tools. By comparing simulated galaxies to the real M104, astronomers can refine their models, narrowing down the possible explanations for dark matter. Some theories propose particles such as WIMPs, weakly interacting massive particles, while others suggest entirely new frameworks for physics, such as modified Newtonian dynamics, MOND, or higher dimensional effects. Beyond its dark matter halo, the Sombrero galaxy's luminous central bulge offers a glimpse into the mysterious relationship between galaxies and their supermassive black holes. Unlike the Milky Way's black hole, which has a mass of around 4 million suns, M104's black hole tips the scales at a staggering billion solar masses. This vast difference raises critical questions. how do these behemoths grow so massive? Are they seeded by smaller black holes formed in the early universe, or do they grow primarily by consuming gas, stars, and even other black holes during galactic mergers? The black hole in M104 is remarkably quiet compared to the so-called quasars found in distant galaxies, where supermassive black holes voraciously consume matter, emitting blinding light across the universe. The Sombrero's subdued activity suggests it is in a dormant phase, but its past may have been far more dramatic. The surrounding globular clusters, relics from an earlier cosmic epoch, may hold the answers. These clusters could contain stars that bear the chemical fingerprints of intense energy outputs, such as those associated with an active black hole. Studying these clues could rewrite our understanding of galactic life cycles. The galaxy's dust lane, the dark band encircling its luminous core, is another area of intense scientific focus. These dense clouds of interstellar dust and gas are more than just visual features, they are the raw material for star formation. When gas clouds within these regions collapse under gravity, they ignite nuclear fusion, giving birth to new stars. Yet the process is far from straightforward. Magnetic fields, turbulence, and radiation pressure all compete to determine whether a star will form or the cloud will remain stable. Astronomers use advanced telescopes, such as the Atacama Large Millimeter/Submillimeter Array, ALMA, to probe these regions in exquisite detail. By observing the faint emissions from cold molecules, they can map the distribution and motion of gas in the dust lane. These observations reveal regions where new stars are likely to emerge and help answer broader questions about how galaxies like M104 sustain star formation over billions of years. But the Sombrero galaxy does not exist in isolation. Like all galaxies, it is influenced by its environment. The interplay between galaxies and their surroundings, known as galactic ecology, is a burgeoning field of study. In the dense environment of the Virgo supercluster, gravitational interactions between galaxies can strip away gas, disrupt star formation, or trigger bursts of new activity. While the Sombrero appears relatively undisturbed, faint streams of stars or gas, known as tidal tails, could betray past encounters with smaller galaxies. These interactions are cosmic fingerprints, evidence of the dynamic forces shaping the universe on the largest scales. The Sombrero galaxy also inspires speculation about the potential for extraterrestrial life. Within its disk, where stars are concentrated, there may be countless planets orbiting sun-like stars. Recent discoveries of exoplanets have shown that planets are more common than once believed, with many residing in the so-called habitable zone, the region around a star where conditions could support liquid water. Could some of these planets harbor life, perhaps even intelligent civilizations? If so, how would they perceive their place in the universe? And might they, like us, gaze at neighboring galaxies in awe, wondering if they are alone? The search for life extends beyond direct observation. Scientists study the chemical evolution of galaxies to understand the distribution of elements necessary for life. The Sombrero's globular clusters, for instance, contain ancient stars that formed when the universe was dominated by hydrogen and helium. Over time, nuclear fusion within stars has produced heavier elements, carbon, oxygen, nitrogen, the building blocks of life. By examining the Sombrero's chemical composition, astronomers can trace the processes that enriched its stars and planets with these life-sustaining elements. The future of galactic research promises even more profound discoveries. The next generation of telescopes, such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA), will provide unprecedented sensitivity and resolution. These instruments will allow scientists to study galaxies not just as they are today but as they were billions of years ago, when the first structures in the universe were forming. By observing galaxies like M104 in greater detail, we can piece together the history of the cosmos itself. The Sombrero Galaxy, with its serene beauty and hidden complexities, is a microcosm of the universe. It is a place where the forces of nature, gravity, radiation, magnetism, interact on scales both vast and minute. It is a testament to the ingenuity of humanity that we can observe and study such distant objects, deciphering their secrets from the faint light that reaches us across millions of years. And yet, for all that we have learned, the Sombrero Galaxy remains a mystery, a beacon of the unknown, urging us to continue exploring, questioning, and dreaming. The universe, it seems, always has more to reveal. The Sombrero Galaxy, despite its iconic appearance and relative proximity in cosmic terms, is a gateway to understanding phenomena that stretch the limits of human comprehension. Its features, ranging from its enigmatic supermassive black hole to its delicate dust lanes and ancient halo, are not isolated wonders but interconnected pieces of a grander cosmic puzzle. Each revelation about M104 serves as a stepping stone toward answering some of the universe's most fundamental questions, while simultaneously opening new doors of inquiry. Supermassive black holes, like the one at the center of the Sombrero Galaxy, remain one of the most perplexing and captivating phenomena in astrophysics. While these gravitational giants were once thought to be mere byproducts of galactic formation, recent studies suggest they may play a central role in shaping their host galaxies. Observations of M104 reveal a paradox: its central black hole is quiescent, yet the galaxy around it shows no signs of the violent upheaval often associated with such massive objects. Could this black hole have been more active in the past, shaping the Sombrero's structure through energetic jets and winds? Or is it lying dormant, awaiting a fresh influx of matter? Simulations of galaxy evolution have demonstrated that feedback from supermassive black holes, where high-energy radiation and winds push out surrounding gas, can regulate star formation. This process, known as AGN, active galactic nucleus feedback, prevents galaxies from growing uncontrollably large. The Sombrero Galaxy's bright, tightly packed core suggests a history of intense activity, even if that activity has now subsided. By studying the chemical signatures in its central region, astronomers can reconstruct its history, searching for evidence of ancient outbursts that may have shaped its luminous bulge and serene outer disk. One of the most fascinating aspects of studying galaxies like the Sombrero is the field of galactic archaeology, the attempt to unravel a galaxy's history by studying its oldest components. The Sombrero's globular clusters, densely packed groups of ancient stars, are particularly valuable in this effort. These clusters are time capsules, preserving the conditions of the early universe when they first formed. By analyzing their metallicity, the abundance of elements heavier than hydrogen and helium, scientists can infer how and when the Sombrero Galaxy enriched itself with heavier elements. Interestingly, the Sombrero Galaxy's globular clusters show a bimodal distribution. Some are rich in heavy elements, while others are metal poor. This suggests that the galaxy may have grown through both internal star formation and external mergers with smaller galaxies. Each merger would have introduced new stars, gas, and dark matter, contributing to the galaxy's current structure. This duality makes M104 a prime example of how galaxies evolve through a combination of peaceful accretion and violent interactions. The Sombrero's prominent dust lane is not just a visual feature, it is a critical clue to its inner workings. This lane, composed of cold gas and dust, is where star formation occurs. However, unlike the well-defined spiral arms of galaxies like the Milky Way, the Sombrero's disk appears smooth and featureless. This raises intriguing questions. Is the dust lane a relic of a more active past, or is it the result of a unique process that inhibits the formation of distinct spiral patterns? Infrared observations have revealed that the dust lane contains a surprising amount of cold gas, the raw material for star formation. Yet, star formation in the Sombrero galaxy is relatively subdued compared to more active galaxies. This suggests that something is suppressing the process, possibly the influence of its central black hole or the galaxy's unique gravitational dynamics. Understanding why star formation varies so widely between galaxies, and even within different regions of the same galaxy, is a key challenge in astrophysics. Zooming out, the Sombrero galaxy is not an isolated entity but a part of the cosmic web, a vast network of galaxies, dark matter, and intergalactic gas that defines the large-scale structure of the universe. The Virgo supercluster, where M104 resides, is a bustling hub of activity, with galaxies interacting through gravitational forces. While the Sombrero appears relatively undisturbed, its history may include past interactions with nearby galaxies or even entire galaxy groups. These interactions can leave subtle imprints, such as streams of stars or gas extending from the galaxy's disk. These tidal features, though faint, are invaluable for reconstructing a galaxy's past. Observations of the Sombrero at extremely low surface brightness levels could reveal such features, offering new insights into its history of mergers and interactions. The Sombrero galaxy, like all galaxies, holds the story of the universe within its stars and structures. Its oldest stars, formed less than 1 billion years after the Big Bang, contain the chemical fingerprints of the first supernovae, which forged the heavy elements essential for life. By studying the light from these ancient stars, astronomers can trace the chemical evolution of the cosmos, linking the formation of galaxies to the broader history of the universe. Furthermore, the Sombrero's striking resemblance to a hybrid of elliptical and spiral galaxies challenges traditional classification schemes. This hybrid nature may be the result of unique conditions during its formation, providing clues about the diversity of galactic evolution. Could the Sombrero represent a transitional stage between different galactic types? Or is it an entirely unique entity, shaped by forces we have yet to understand? The Sombrero galaxy's mysteries are not merely academic, they drive technological innovation and international collaboration. Upcoming missions, such as the Nancy Grace Roman Space Telescope, aim to map the universe's structure with unprecedented detail, shedding light on dark matter and the role of galaxies like M104 in the cosmic web. Ground-based telescopes like the Extremely Large Telescope, ELT, will peer deeper into the Sombrero's core, revealing the dynamics of its black hole and surrounding stars. Meanwhile, instruments like the Square Kilometre Array, SKA, will revolutionize our understanding of the intergalactic medium, the diffuse gas that connects galaxies. By studying how this gas interacts with galaxies like the Sombrero, scientists hope to uncover the processes that fuel star formation and regulate galaxy growth. As we gaze at the Sombrero galaxy, we are reminded of the boundless potential of the cosmos. Each discovery about M104 is not just a step forward in science, it is a testament to humanity's ability to question, to explore, and to dream. The Sombrero is more than a galaxy, it is a symbol of the universe's endless capacity for wonder, complexity, and beauty. And as our tools grow more powerful and our theories more refined, the mysteries of M104 will continue to inspire the next generation of explorers, thinkers, and dreamers. The universe, vast and unfathomable, continuously reveals glimpses of its complexity, and among its celestial wonders, the Sombrero Galaxy stands out as a masterpiece of natural architecture. It beckons us not just with its beauty but with the secrets it holds, secrets that push the limits of our understanding and ignite our deepest curiosities. From the silent movements of its stars to the hidden forces shaping its evolution, the Sombrero Galaxy is a story waiting to be unraveled, a puzzle woven with threads of time, gravity, and light. Imagine standing at the edge of its luminous disk, surrounded by billions of stars, each one potentially hosting planets. The thought alone is staggering. What would those worlds look like? Could there be a planet with intelligent beings gazing back at their version of the cosmos, wondering if they too are part of something greater? The search for extraterrestrial life isn't just about finding biological traces, it's about connecting with something fundamentally universal, bridging the gap between what we know and what might be. The light we see from the Sombrero Galaxy today began its journey 31 million years ago, traveling across the silent expanse of space to reach our eyes. During that time, life on Earth evolved from early mammals to the dominance of humans. This simple fact, that light serves as both a messenger and a time machine, underscores the profundity of astronomical observation. Every photon captured in our telescopes carries with it the history of the galaxy, encoding events we are only now beginning to decipher. The intricate balance that allows galaxies like the Sombrero to exist is awe-inspiring. Gravity pulls stars inward, binding them into their orbits, while angular momentum prevents collapse, maintaining the graceful structure we observe. But beneath this apparent order lies chaos. Stars are born from collapsing clouds of gas, while others meet fiery ends as supernovae, scattering their enriched remains across the galaxy. These explosions forge the heavy elements essential for life, spreading them into interstellar space to be incorporated into new stars, planets, and perhaps even living beings. Every atom in your body was once part of a star that lived and died billions of years ago. This cosmic recycling connects us not just to the Earth but to the stars themselves. The Sombrero Galaxy's dust lane, dark and enigmatic, is more than a striking visual feature, it's a dynamic region where stars are actively forming. But why does the galaxy's star formation appear subdued compared to more active galaxies? Is it nearing the end of its life cycle as a star-forming system? Or is it in a delicate equilibrium, sustaining itself without the dramatic bursts of energy seen in younger galaxies? These questions are not just about understanding M104, they are about comprehending the life cycles of galaxies as a whole. The halo of the Sombrero Galaxy, vast and filled with ancient globular clusters, is another source of fascination. These clusters contain some of the oldest stars in the universe, formed when the cosmos was young and dominated by primordial gas. Studying them is like looking at a photograph of the universe in its infancy. What stories do these stars tell? What conditions led to their formation, and how have they survived for billions of years? The answers may reveal not just the history of the Sombrero but also the broader narrative of galactic evolution. Dark matter, the invisible glue that holds galaxies together, adds another layer of intrigue. The Sombrero Galaxy's rotation curve, How its stars move at various distances from the center defies the predictions of Newtonian physics, pointing to the existence of dark matter. But what is dark matter? Is it composed of exotic particles, or does it hint at a fundamental flaw in our understanding of gravity? Experiments around the world are racing to answer these questions, but for now, the sombrero remains a testament to the unseen forces that shape the cosmos. At its core lies a supermassive black hole, a gravitational monster whose presence defies comprehension. Unlike stellar mass black holes, which form from collapsing stars, these supermassive counterparts seem to have existed since the earliest epochs of the universe. How did they form so quickly? Were they seeded by the first stars, or did they grow through mergers and accretion over time? The sombrero's black hole is relatively quiet today, but its past may hold clues to these questions. Could it have once been a quasar, blazing with energy as it devoured surrounding matter? And if so, how did it transition to its current dormant state? The Sombrero galaxy also challenges our traditional classifications of galaxies. It exhibits features of both spirals and ellipticals, blurring the lines between these categories. This duality suggests a complex history, possibly involving mergers with smaller galaxies or interactions with neighboring systems. What processes led to this hybrid structure? Was it a slow, steady accumulation of matter, or a more chaotic series of events? Understanding these dynamics could reshape how we think about galaxy formation and evolution. Looking beyond the galaxy itself, we are reminded that it is part of a vast cosmic network. Galaxies are not isolated islands but are connected through the gravitational filaments of the cosmic web, a structure that spans the observable universe. The Sombrero galaxy, nestled within the Virgo supercluster, interacts with this web, influencing and being influenced by its neighbors. These interactions, though subtle, leave lasting imprints, shaping the galaxy's evolution over billions of years. And yet, for all its grandeur, the Sombrero galaxy is just one of trillions. Each galaxy, from the smallest dwarf systems to the largest ellipticals, tells its own story. Together, they form a mosaic of the universe, a tapestry woven with threads of light, matter, and time. The sombrero is a single thread in this tapestry, but it is a thread rich with detail and meaning, a reminder of the complexity and beauty that defines the cosmos. As we continue to study the Sombrero galaxy and its counterparts, we are not just learning about distant objects, we are uncovering the mechanisms that govern the universe itself. Each discovery, no matter how small, brings us closer to understanding the origins, structure, and ultimate fate of the cosmos. The Sombrero galaxy is a beacon of wonder and a challenge to our intellect, inviting us to look deeper, think broader, and dream bigger. In its light, we find not just answers, but the inspiration to keep asking questions. The Sombrero galaxy, though seemingly serene and static from our distant vantage point, is in reality a dynamic and evolving entity, a microcosm of the universe's ceaseless activity. Beneath its tranquil facade lies a realm where stars are born and die, where invisible forces like dark matter sculpt its shape, and where the echoes of cosmic history reverberate across billions of years. Its very existence challenges us to confront the profound mysteries of space, time, and the nature of reality itself. The supermassive black hole at the heart of the Sombrero galaxy, with a mass exceeding 1 billion suns, is a gravitational colossus whose sheer presence shapes the galaxy around it. Despite its dormancy, it exerts an invisible but profound influence, orchestrating the motion of nearby stars and gas clouds. Scientists theorize that such black holes may act as cosmic regulators, their energy output capable of either fueling or quenching star formation. Could this black hole's quiet nature be a sign of a galaxy in equilibrium, or is it the calm before another epoch of activity? Observing its subtle gravitational effects allows astronomers to probe the depths of the unseen, peeling back layers of cosmic history encoded in the orbits of the surrounding stars. The dust lane that encircles the Sombrero galaxy, striking against the bright core, is not merely a backdrop to this cosmic wonder, it is an active, ever-changing environment where the building blocks of stars and planets reside. Molecular clouds within the lane, dense with gas and dust, are the nurseries where new stars are formed. Yet, the conditions for star birth are precarious, dependent on a delicate balance between gravitational collapse and the disruptive forces of turbulence, magnetic fields, and radiation pressure. Observing this process in detail with advanced telescopes reveals the intricate interplay of physics that governs the creation of stars, shedding light on how galaxies like the Sombrero maintain their luminous populations over billions of years. Further out, the Sombrero's vast halo is a region of intrigue, filled with ancient globular clusters and an abundance of dark matter. These clusters are fossilized remnants of the early universe, their stars formed from the primordial gases that existed shortly after the Big Bang. Each globular cluster is a snapshot of cosmic time, and their varying compositions hint at the galaxy's complex history of growth and interaction. The Sombrero's halo is unusually rich in such clusters, suggesting it has undergone a unique evolutionary path. Did it absorb smaller galaxies during its formation, each contributing its own cluster population? Or did it form in isolation, building its halo through internal processes alone? One of the most tantalizing mysteries of the Sombrero galaxy lies in its hybrid nature. Its bright, spherical bulge is characteristic of elliptical galaxies, while its thin, well-defined disk aligns with the properties of spiral galaxies. This duality defies easy classification, prompting questions about its formation. Did it begin as a spiral galaxy that later accumulated a massive central bulge? Or was it an elliptical galaxy that developed a disk through subsequent interactions? The answer may lie in the galaxy's stellar populations. By analyzing the ages, compositions, and motions of its stars, astronomers can reconstruct its evolutionary journey, piecing together a narrative that spans billions of years. Beyond the Sombrero galaxy itself, its context within the larger universe adds another layer of fascination. Galaxies are not solitary wanderers, they exist within a vast and intricate web of matter and energy. The Virgo supercluster, where the Sombrero resides, is one of the largest known structures in the cosmos, its galaxies interconnected by the gravitational pull of dark matter. These cosmic filaments, invisible to the naked eye, form the scaffolding of the universe, dictating the motion of galaxies and the flow of gas between them. The Sombrero's position within this web influences its evolution, as the gravitational tides of nearby galaxies subtly shape its structure and star formation activity. The discovery of dark energy has added yet another layer of complexity to the study of galaxies like the Sombrero. This mysterious force, responsible for the accelerated expansion of the universe, permeates space and affects the trajectories of galaxies on cosmic scales. While dark matter binds galaxies together, dark energy pushes them apart, creating a delicate cosmic tug-of-war. Observations of the Sombrero and its neighbors provide critical data for understanding the interplay of these forces, offering clues about the ultimate fate of the universe. Will the cosmos continue to expand forever, growing colder and darker as galaxies drift apart? Or will it reverse course, collapsing in a dramatic, big crunch? Despite the Sombrero's apparent tranquility, its past likely holds tales of dramatic collisions and interactions. Galaxies frequently merge in the cosmic dance, their stars and gas clouds intermingling in events that can trigger bursts of star formation or feed central black holes. The Sombrero's hybrid structure may be the result of such interactions, each one leaving behind subtle traces in the form of tidal streams, warped disks, or unusual stellar populations. Advanced imaging techniques, capable of detecting the faintest features, are beginning to uncover these hidden scars, providing a window into the chaotic processes that shape galaxies over time. In the search for life beyond Earth, the Sombrero galaxy also plays a symbolic role. Within its disk, billions of stars may host planetary systems, some of which could harbor the conditions necessary for life. The discovery of exoplanets within our own galaxy has revealed a staggering diversity of worlds, from Earth-like planets in habitable zones to gas giants with exotic atmospheres. If planets in the Sombrero galaxy share similar characteristics, they could be home to entirely different forms of life, shaped by the unique conditions of their environments. While direct exploration of these distant systems remains beyond our reach, their potential inspires us to continue searching for our cosmic neighbors. As technology advances, so too does our ability to study galaxies like the Sombrero in unprecedented detail. Instruments like the James Webb Space Telescope and the Extremely Large Telescope promise to revolutionize our understanding of the cosmos, allowing us to peer deeper into the universe and uncover the processes that govern its evolution. These tools will enable us to study not just the Sombrero's stars and gas, but the very fabric of space-time itself, probing phenomena such as gravitational waves and the nature of dark matter. The Sombrero galaxy is more than a celestial object, it is a reminder of the vastness and complexity of the universe. It invites us to question, to explore, and to dream, challenging us to look beyond our immediate surroundings and consider our place in the cosmos. Each discovery about the Sombrero is a step closer to understanding the universe's grand design, yet it also serves as a humbling reminder of how much remains unknown. In its light, we find not just answers but the inspiration to continue the journey of discovery, fueled by the unquenchable curiosity that defines us as a species. The Sombrero galaxy continues to captivate not just as a celestial wonder, but as a symbol of the universe's boundless complexity and mystery. The more we study it, the more we realize how deeply interconnected its components are, and how they reflect the larger processes at play throughout the cosmos. It is a galaxy that defies simple classification, a hybrid of elegance and enigma, inviting us to unravel its secrets. The galaxy's core, shining like a brilliant lighthouse in the dark sea of space, tells the story of incredible forces at work. Supermassive black holes like the one at the center of the Sombrero are known to influence their surroundings in profound ways. Though this particular black hole is dormant now, scientists believe it may have once been an active galactic nucleus, a quasar so luminous that it could have outshone the entire galaxy for millions of years. Such energy bursts would have had the power to reshape the galaxy's structure, pushing gas outward and halting star formation while enriching the intergalactic medium with heavy elements forged in the stars. But why has the black hole gone quiet? Could it reignite in the future? Black holes feed on matter, and if new material, gas, dust, or even an entire star, wanders too close, the dormant giant could awaken in a spectacular blaze. Observations from the latest generation of X-ray and infrared telescopes may reveal signs of this slow-motion drama, showing subtle shifts in the black hole's environment that could signal its next act. The Sombrero Galaxy's unique dust lane is another source of intrigue. Dust, often thought of as a nuisance obscuring stars, is actually one of the most important ingredients in the universe. It is within these dense regions of gas and dust that stars are born. But why is the Sombrero's dust lane so sharply defined? Most spiral galaxies exhibit sweeping, winding arms rich in star-forming regions, yet the Sombrero's disk remains relatively featureless, almost minimalist. Could it be the result of a past merger that redistributed the galaxy's material into this unusual configuration? Or is it governed by internal forces, such as the gravitational effects of its dark matter halo or the influence of magnetic fields threading through its disk? The halo of the Sombrero Galaxy offers an entirely different perspective. Extending far beyond the visible disk, this halo is a vast sphere of influence, populated by ancient globular clusters and infused with dark matter. It is a treasure trove of information about the early universe. Each globular cluster, a compact group of stars bound by gravity, acts as a fossil, preserving the conditions of the universe as it was billions of years ago. These clusters formed before the Sombrero Galaxy itself took shape, providing clues to the processes that led to galaxy formation. One of the most compelling features of the halo is its connection to the concept of galactic archaeology. By studying the motions, compositions, and ages of the stars and clusters in the halo, astronomers can reconstruct the galaxy's formation history. They can identify remnants of smaller galaxies that were absorbed into the Sombrero over billions of years, tracing the paths of these ancient cosmic collisions. These mergers are not just violent events, they are also creators, seeding the galaxy with new stars, enriching its gas with heavy elements, and contributing to the growth of its central black hole. The Sombrero Galaxy's place within the cosmic web adds yet another layer of intrigue. This web, an intricate network of galaxies, dark matter, and intergalactic gas, is the universe's scaffolding, dictating the movement and evolution of galaxies on the largest scales. The Sombrero, situated within the Virgo supercluster, interacts subtly with its neighbors through gravitational forces. These interactions may strip away gas, ignite bursts of star formation, or leave faint tidal streams, ethereal trails of stars torn from other galaxies. Searching for these faint imprints requires the most sensitive telescopes, capable of detecting light billions of times fainter than the night sky. While the Sombrero Galaxy is a wonder in its own right, it also serves as a key to understanding broader phenomena, such as the nature of dark matter and dark energy. Dark matter, the unseen mass that holds galaxies together, is evident in the Sombrero's rotation curve, how its stars move at different distances from the center. The outer stars orbit far faster than they should based on visible matter alone, revealing the presence of a massive, invisible halo of dark matter. But what is this mysterious substance? Experiments on Earth are attempting to detect dark matter particles directly, while cosmological simulations use galaxies like the Sombrero to refine their models of how this invisible matter shapes the universe. Dark energy, even more mysterious than dark matter, governs the expansion of the universe itself. Observations of galaxies like the Sombrero provide critical data for understanding this enigmatic force. By measuring the distances and velocities of galaxies, scientists have discovered that the universe is expanding at an accelerating rate, driven by dark energy. The implications are profound. If dark energy continues to dominate, the universe could end in a big freeze, where galaxies drift so far apart that their light can no longer reach each other, leaving a cold, dark cosmos. Galaxies like the Sombrero may hold clues to how this process unfolds and what it means for the future of the universe. Yet, even as we grapple with these grand questions, the Sombrero galaxy invites us to consider the possibility of life beyond Earth. Within its disk, billions of stars may host planetary systems, some of which could have the conditions necessary for life. The search for exoplanets in our own galaxy has revealed a stunning variety of worlds, from Earth-like planets to gas giants with exotic atmospheres. If life exists in the Sombrero galaxy, it could take forms we cannot even imagine, shaped by environments vastly different from those on Earth. The idea that intelligent beings may be observing their version of the universe from within M104 is both humbling and exhilarating. As our telescopes become more powerful and our computational models more sophisticated, the mysteries of the Sombrero galaxy will continue to unfold. Each discovery adds a new layer to our understanding, not just of this particular galaxy, but of the universe as a whole. The Sombrero is a reminder that science is a journey, one fueled by curiosity and driven by a desire to explore the unknown. In its light, we are connected to something far greater than ourselves, a cosmos that is as vast as it is beautiful, as mysterious as it is inspiring. The Sombrero galaxy stands as a beacon in the night sky, urging us to keep looking upward, to keep questioning, and to keep searching for our place in this extraordinary universe. It is not just a galaxy, it is a reflection of the infinite possibilities that await us, a reminder that the greatest discoveries may still lie ahead. The Sombrero galaxy, M104, serves as a cornerstone for scientific research, offering insights into some of the most profound mysteries of astrophysics. From its unique structural features to the underlying forces that govern its evolution, the Sombrero represents a microcosm of the complex processes shaping the universe. Ongoing research into this galaxy not only enhances our understanding of its distinct characteristics but also sheds light on universal phenomena that apply to galaxies throughout the cosmos. Dark matter remains one of the most perplexing and significant subjects in astrophysics. Observations of the Sombrero galaxy's rotation curve provide compelling evidence for its existence. The stars and gas in the galaxy's outer regions orbit far faster than they should if only visible matter were present. This discrepancy suggests the presence of an enormous halo of unseen mass enveloping the galaxy. To probe this enigmatic force, scientists use sophisticated simulations that mimic the behavior of galaxies with varying dark matter distributions. By comparing these models to observations of the Sombrero galaxy, researchers refine theories about the properties of dark matter. Some experiments, like those conducted at the Large Hadron Collider or deep underground detectors, aim to directly detect dark matter particles, while others focus on its indirect effects, such as gravitational lensing. In the case of the Sombrero galaxy, its massive halo bends the light of background objects, providing another way to study the elusive substance shaping its structure. The Sombrero's prominent dust lane is a site of ongoing star formation, though at a subdued rate compared to more active galaxies. Recent studies using telescopes like ALMA, Atacama Large Millimeter/Submillimeter Array, have revealed intricate details of the molecular gas within this lane. Molecules like carbon monoxide, CO, which emit radio waves detectable at millimeter wavelengths, serve as tracers for the cold gas essential for star birth. These observations have highlighted pockets of dense gas where gravitational forces are overcoming internal turbulence, leading to the formation of new stars. Understanding why the rate of star formation in the Sombrero galaxy is relatively low compared to other spiral galaxies is a critical area of research. It could be due to environmental factors, internal feedback from the galaxy's central black hole, or the influence of its dark matter halo. The Sombrero galaxy's bright bulge and extended halo make it an excellent target for studying chemical evolution. By analyzing the light spectra of stars in these regions, astronomers can determine their chemical compositions, ages, and motions. This data provides a timeline of the galaxy's enrichment with heavy elements produced in supernovae and other stellar processes. The Sombrero's halo, populated with thousands of globular clusters, contains some of the oldest stars in the universe. These clusters are relics from an earlier era, formed when the universe was still dominated by hydrogen and helium. By studying their metallicity, the abundance of elements heavier than helium, researchers can infer the conditions of the early universe and the processes that led to the galaxy's formation. The bimodal metallicity distribution observed in the Sombrero's globular clusters suggests a history of both internal star formation and external mergers, providing critical clues about its evolutionary path. At the heart of the Sombrero galaxy lies a supermassive black hole with a mass of approximately 1 billion suns. Studying this gravitational giant provides insights into the relationship between black holes and their host galaxies. Observations of the stars and gas orbiting close to the black hole reveal its mass and influence on the surrounding region. One area of interest is the role of the black hole in regulating star formation. Through a process known as feedback, energy released by the black hole can heat or expel gas, suppressing star formation. While the Sombrero's black hole is currently dormant, its past activity may have played a critical role in shaping the galaxy's structure. High-resolution X-ray and infrared observations are being used to search for evidence of past outbursts, such as shock waves in the surrounding gas or unusual chemical signatures. The Sombrero galaxy's classification as a hybrid between a spiral and an elliptical galaxy makes it a fascinating subject for theoretical modeling. Spiral galaxies typically have prominent disks with well-defined arms, while elliptical galaxies are characterized by their spherical or oval shapes and lack of disk structures. The Sombrero, with its bright bulge and extended disk, exhibits features of both. Theories suggest that this hybrid structure may result from a combination of internal dynamics and external interactions.